Welcome back to our web series, A Comprehensive and Intuitive Introduction to Deep Learning. We are in season 3, where we'll be studying large language models and the transformer neural network architectures that power them. This is episode 2 of season 3. In today's episode, I will go into the details of encoder-only large language models. We'll explore everything from how you pre-train them, how you fine-tune them, and then how you use them to build some killer applications. So in the previous episode, I showed you the timeline of the key innovations that led to large language models. And I said that the attention is all you need paper, which is the seminal paper which came out in 2017, is the one that proposed the transformer neural network architecture. And the transformer neural network architecture changed how natural language processing tasks were performed. An year after this paper was published, there were two teams, one from OpenAI, led by Radford, who explored using the decoder only part of the transformer architecture to build large language models that could generate text. And a separate team, led by Devlin at Google, explored using the encoder only neural network architecture to build large language models that do not generate text, but that can be used to do other compelling natural language processing tasks like classification, sentiment analysis, extractive summarization, labeling, and so on. So we will study this second form of large language model in today's episode. So we'll focus on BERT. BERT is a encoder only large language model. Before we get into seeing what BERT is or how it is architected, let's try to understand what are the compelling applications one could build if you had an encoder only large language model. Everybody understands that if you have something like a GPT type large language model, you could generate text. But what is it that you could do with just an encoder only large language model that does not generate text? You could actually build some compelling applications. For example, you could build a knowledge hub where the encoder only large language model can automatically classify the articles that you're publishing into this knowledge hub based on the categories that they belong to. It can also label them appropriately. Like, for example, if it's a technical knowledge hub that you're creating to capture Kubernetes related content, then it can categorize them into different groups like networking or storage or security and so on. And then for each of the articles that are being published, it can automatically go and label them or tag them. Is it related to operations? Is it related to production deployment? Is it related to observability? And so on. It can also classify that into, is it talking about a topic that is advanced or is it talking about a topic that's more foundational? So just think about it this way. You're just uploading articles and you have automatically this grouping and categorization and labeling. You could also use that to extract certain entities from blocks of text. For example, if you were to give it a text and you say, hey, I want you to automatically extract any names of people that are there in this text, or names of any countries or cities or phone numbers or website URLs or addresses or animals or what have you. You decide what are the type of entities you would like to extract, and you could use an encoder only large language model to do that automatically. You could also use that to do duplicate detection or similarity recommendation. So think about it this way. Let's say you are in a website like Quora or on Stack Overflow. And when somebody asks a question and you're browsing through one of those things, you'd also like to see other questions that are similar to the question that is being asked or the question that is being answered. That's very powerful because whether it is things like Quora or Stack Overflow, or whether it is a customer success portal where you're capturing customer issues, where you would like to capture things that are similar to issues that are already solved in the past, it's very compelling. It creates a very delightful customer experience. So you could actually create those kind of applications as well using an encoder only large language model. So the key idea for the encoder only large language model did not come from the attention is all you need paper. It actually came from this paper that was published about a year later called BERT. BERT stands for Bidirectional Encoder Representations from Transformers. And this is considered to be a landmark paper in the world of natural language processing. And there are two reasons for that. Number one is, even before transformers and the large language model movement started, people were doing text classification. You would do entity recognition and things like that. But what BERT allowed us to do is do that with more precision, more accuracy, more performance, and more correctness. And as a result, it became the state of the art for most natural language processing tasks when it came to things like classification and entity extraction and similarity detection and things like that. The second reason why it is a landmark paper is because this is the paper that introduced the concept of splitting training into two steps. One step is called pre-training and the other step is called fine-tuning. And I will talk about what those two things mean shortly. But this is the paper that introduced that concept. And since then, whether it is the encoder-only large language models or it is the decoder-only large language models like GPT and Grok and Llama and so on, all of them split the training into pre-training and fine-tuning steps. Now let's get into the details of how you would train and then use a encoder-only large language model. But before we get there, I think it's important that we do a very quick recap of the encoder-only transformer neural network architecture. I'm just giving you the very high-level overview here. I did almost a 2-hour presentation in episode 1 of season 3, and I go into a lot of intuition and a lot of examples in that. So if you have not followed that, I would encourage you to go back and look at that. But for continuity reasons, I'm going to do a very quick recap here, and then we can build on top of that. So an encoder-only transformer architecture looks like this. You would feed it text from the bottom, which gets tokenized, and those tokens basically get fed into what a layer where you would extract the word embeddings for each of those tokens. And remember, word embeddings is extracting the feature dimensions of each token, and you would determine how many features you would like to extract. Let's say D number of features, then you would have for each token you would have D slots, and each slot would represent a particular feature of that token or the word. And then it also gets fed into a positional encoding layer, which will assign unique position IDs for the position in which that token appears in that text. Now, both of them are added together, and then you create a S cross D size matrix. S is the sequence length, which is the total number of tokens that you have in your input text. And D is the total number of dimensions, which are the number of features that each of those tokens has. Now, that gets fed into the encoder-only transformer. It goes through a first layer called multi-head attention, where you do self-attention. And self-attention, I'll go into a lot of details, is a way in which you change the embedding matrix that is coming in a contextual manner. So for example, I show you here, if you have a sentence, I walked into Apple store eating an apple. The word apple, without contextually changing the embeddings, would have the same feature dimensions, both for the first occurrence, which is this occurrence in the sentence, as well as the second occurrence, which is this occurrence in the sentence. However, as humans, we know that the first occurrence of the word apple is referring to the company, not the fruit. And the second occurrence is actually referring to fruit and not the company. So I go into the details of how you could train a neural network to understand these details. But it happens in the multi-head attention layer of the encoder-only transformer. And the job of this layer is to adjust the embedding vectors so that in the context in which these words appear, certain dimensions are amplified and certain dimensions are reduced in value. And then it goes to this projection layer called feed-forward layer, and then it goes through layer normalization, and then you have residual skip connections and so on. Anyway, so we covered all this. But the key thing to understand here is that text goes in and you generate the embedding matrix, which is S cross D. And what comes out of the encoder-only transformer is a contextually updated embedding matrix, where, as I said, like for example, if you take this sentence, this occurrence of apple will get its company features amplified and its fruit features suppressed. Whereas the second occurrence of the word apple, its company features get suppressed and its fruit features get amplified. Okay, this is all great, but how do you train this? And that's where we left episode 1. So when you want to train something, you obviously need input, and we know that the input could just be text. But they also need to know what is the ground truth value against which you will test the prediction that the neural network makes. So in this case, what is that ground truth value, the y true value? And then how do you predict the y pred so that you can compare the two? And what would be the appropriate output function and what is the loss function? So this is what we'll study in this episode in terms of how you train. And when you're training, how do you determine what is the x, the y true, the y pred, output function, and the loss function? Okay. So the first step to build a encoder-only large language model is to do what is called as pre-training. Remember, I told you that the BERT paper is a landmark paper because it introduced the concept of training by splitting it into two steps. The first step is called pre-training. In pre-training, what you do is you take an encoder-only transformer with the weights initialized to random values, and then you attach what we call as a pre-training head. Now, this is important because if you think about it, the encoder-only transformer really does not have anything that forces in the back propagation a way in which you could calculate the loss and then start adjusting the weight so that it produces a good contextual aware embedding matrix. So you need to have something on the top here that can allow us to figure out what the loss is and from a prediction and then start to back propagate errors doing a gradient descent to adjust the weights. So you need to have something like that. That's why you need to have what is called as a pre-training head that you attach on top of this encoder-only transformer. Now, what is the input that you give to this thing? In the pre-training step, you collect as much text as you can get your hands on. Like, for example, the entire internet web crawl data, or you could have, if you have access to books that are not copyrighted, you could get all the books and then give all the text from those books into this and all that. But one of the most important thing to understand here is the pre-training step does not require any human labeling of the data. That is why it's called self-supervised learning, which means that you just feed it text, and depending on how you design your pre-training head, it will figure out the concept of what a loss is, and it will figure out how to start doing back propagation to adjust the weights in the transformer. Now, the pre-training actually typically takes days or months to train. It is typically done on GPUs because it takes a lot of time to go and do this pre-training on a massive amount of text. It does require a massive amount of text. So once it is pre-trained, what gets produced is what is called as a pre-trained encoder-only large language model. So this pre-trained encoder-only large language model has now understood the concept of language. It understands grammar, it understands semantics, it understands which words fit together, which words do not fit together, which sentences fit together, which sentences do not fit together, all of those things. So it pretty much has learned language. It's almost like, let us say, just to take an analogy, let's say that you're training somebody to become a chef. The first set of training is the basic constructs of how you cook, what are things that are compatible with each other, what is it that is not compatible. For example, you cannot mix, let's say, chocolate and fish, right, in a dish, or you cannot mix garlic and coffee in a drink. So those are not compatible. Similarly, you can mix, let's say, spices and meat and those kind of things. So that is what in the pre-training step a chef would learn. Similar to that, in the language world, a pre-trained large language model pretty much understands what sentences are correct, what sentences are not correct, what word formulations are correct, what word formulations are not correct. However, that does not mean that can be used to do things like, let's say, sentiment analysis or classification on labeling. For that, you need one more step. Just like going back to the chef analogy, just because somebody knows what are compatible ingredients, what is the right step in processing food and all that, does not mean that they can become an Italian chef for doing Italian food or chef for doing Indian food or American food. You need to, once they have a basic training on general culinary skills, now you have to fine tune those skills to become specialized on, let's say, Italian cooking or Indian cuisine and so on. So just like that, even for large language models, once you have something that is pre-trained, you take that and then you attach a different, what we call as a task specific head on top of this pre-trained LLM. So you take out the pre-trained head and then you attach a different task specific head. And that task specific head, again, we'll go into a lot of those details shortly, but the task specific head is determined based on what task you're trying to specialize this pre-trained large language model on. For example, if you're trying to build something for classifying the sentiment of tweets or sentiment of movie reviews, then you will have a classification task specific head. Or for example, if you're trying to label news articles like into sports and technology and politics and so on, then you would have a labeling specific task specific head. Or if you're trying to, let's say, figure out similarity between two different documents, then you would have something else, a similarity specific a specific head, and so on. So, and we'll go into all of those details shortly. But you would have something like that, a task specific head, and you put it on top of the pre-trained LLM. And then you would now give data which is now labeled by humans. Because, as I said, the first step, which is pre-training step, is only to build an understanding of language constructs. And for doing that, you really don't need to label anything. That's why it's self-supervised. But if you want to go classify something, that's a very task specific thing. Classification is a task. Then you will need to label and tell the neural network that, okay, as a human, I deem that, for example, this particular movie review says that they like the movie. This particular movie review says that they did not like it. And this one says that this is neutral. So you have to label it. So this is more cumbersome because you have to now take your training data set and label it. That is why it is supervised learning. And you really don't need to have massive amount of data to do fine tuning. Typically, you can have, I would say, hundreds and thousands of records for doing fine tuning. By comparison, for pre training, you would need to have millions, if not billions, of text sentences that you have gathered from all over the internet. Right? And because the fine tuning is working on a smaller set of training data, it takes minutes, hours, or days rather than it takes days or months in the case of a pre-training step. And again, for the most part, fine tuning is also done on GPUs. But if your data is not that complicated in terms of its relationships and all that, sometimes you can also get by with just using CPUs to do this. So once you have fine-tuned it, now you have what is called as a fine-tuned large language model, and that is what you would save. Okay, so what is it that you save? In the first step after pre-training, you would save pre-trained large language model with the pre-training head. Okay, and after you fine-tune, you save the fine-tuned the encoder-only transformer with the weights that are also there in this task specific head. Okay, so this combination becomes your task specific large language model. Let's say a classification based encoder only large language model is this thing. Now this is also called transfer learning. The reason it's called transfer learning is because what you have done is that you transferred the learning of what language means, right, from this pre-training step to the fine-tuning step. Because you're not, let's say you want to do movie sentiment analysis, you don't have to go and teach it language. You don't have to teach humans of constructed English languages. It is already learned that during pre-training. So you're just transferring that learning to doing fine-tuning. So this is the idea of what is called as transfer learning. Okay. So once you have done this, you go and save this pre-trained LLM, and you can also save the fine-tuned LLM. The pre-trained LLM is saved because tomorrow you might say, hey, listen, I would like to fine tune it for a completely different task. So you don't have to go and start training the large language model on language semantics again. You already have this pre-trained large language model. So you can just take that, then attach whatever for that specific task that you would like to fine tune on, attach that task specific head, then fine tune it. And then once you have the fine tuned thing, save that. And once you have the fine tuned large language model, you start doing inferencing on that. And inferencing takes typically milliseconds to seconds. It rarely takes seconds. It actually takes milliseconds. And it can be handled by GPUs, and several times also by CPUs you could do this, because here you're not really going and changing weights and all of those things, right? Okay, so these are the steps that you would do to train a large language model, an encoder-only large language model. Now, what are these heads? So I'll actually explain that using a general abstraction, because the way I want you to learn this is not just to see what was done by somebody else, but to kind of approach it from first principles, right? Which is, how do you think about a problem, and then how do you translate that problem into a solution, and that solution being something that arrangement of different components of a deep learning pipeline, so that you can perform a specific task to solve a specific problem, right? So that abstraction that I think is very powerful is to look at it this way. So you have your transformer, encoder-only transformer. So the first thing, so there are four things that you need to understand. The first thing in our abstraction is what I call as a task-specific input layer. So for a given task, how do you format the input, and how do you provide the ground truth value, right? So that you can compare the prediction with the ground truth value. So based on pre-training task or different types of fine-tuning tasks, this input layer changes, and you have to figure that out. The next thing is, as I told you, right, you need to have a task-specific head on the top, and that head is the one that will allow you to make predictions. And I'll show you what those predictions are shortly. So you will need to also think about it in terms of the second abstraction is, what would, for your specific problem that you're trying to solve, how would you design this task-specific neural network head? Once you have a neural network head here, you can predict the output, and that happens through the output function. So what would be the task specific output function? For example, if you're trying to classify something into whether it's a spam, this email is spam or not spam, then that your output function could be a sigmoid function, right? Or if you're trying to do multi-label classification, that your output function would be a softmax. So based on the type of task you're performing, you would have to figure out what is a task specific output function. And then you would also need to have a task-specific loss function. For example, if you're using sigmoid as your output function, then you would use a binary cross-entropy loss as your loss function. If you're using softmax, then you would use a cross-entropy loss function, right? So I think this abstraction is very important to understand, so that You just don't learn what somebody else has done, but you actually understand how to decompose a problem into a solution space and then map it into a neural network architecture pipeline and then fit in whatever you want. So that way, tomorrow, if you want to solve a specific problem, then you just know how to fill in these boxes, these 4 boxes, because the transformer by itself, that remains static. What happens around it will determine what you're going to do with it. What is it that you're trying to solve, or what is it that you're trying to build? Okay, so with that, let's get in and understand step 1. How do you pre-train an encoder-only large language model? And this is done so that you can teach the large language model human language. Okay, so how do you teach a machine to learn human language? Let's look at that, which is step 1. So in this pre-training step, the key goal is to figure out what you put in these 4 parts: the input layer, the task-specific neural network head, and output and the loss function blocks. The key goal also is to go and adjust the weights of the transformer. Okay, so there are 4 strategies to retrain an encoder-only large language model. The first one is called masked language model. Now, before we get into understanding what masked language model is, let's try to understand how a human child would learn language. Now, a human child, I mean, if you just kind of reflect back on our own learning, we did not learn language by memorizing rules. We don't memorizing syntax or grammar rules and all those things. We actually understand and learn language by observing. We hear or read thousands of sentences over our lifetime. Actually, we hear millions of sentences. Some of them are malformed or partial and all those things. And from that, we will try to determine the context in which those sentences are being used. And we'll also determine what sentences are not correct in certain contexts, what sentences are correct, what word formulations are correct, and what word formulations are not correct. And based on that, the biological neural networks in our brain are trying to abstract out all the rules. So the language itself has these rules that nobody is giving us. Yes, we have studied grammar, but just because we studied grammar is not how we are actually learned languages, right? We have mostly learned languages by observation. Okay. And given what is happening, you can infer the meaning of a word. And if a word is not given, you can substitute based on what's happening, the context. You can go and fill in that blank and figure out if this is perhaps the word that makes the most sense and so on. That is how a human will learn language. Now we want to mimic this kind of a learning in a machine. Okay. And that is what masked language model does. What a masked language model does is pretty straightforward. You take sentences and you mask certain words in the sentences and you make the encoder-only transformer predict what is that word that you have masked. And in that prediction, it will start to understand the rules that humans have subconsciously defined word arrangements to form sentences. Okay, so for that you will need to know those 4 things: which, what is the, how do you pass the input, and how do you put this pre-training head, and so on. So let's look at that now. So you have your encoder-only transformer. The weights are all initialized to random. First step is that you take a text from your training data set. What is this training data set? It is the entire web crawl of the internet. You don't have to label it. You just have to just take those texts. Then you tokenize it, and then you randomly mask certain tokens or certain words in this input. Okay, and you keep a copy of what are those words that you marked. For example, here the input is the cat sat on the mat, and randomly you have figured out that I'm going to mask cat and I'm going to mask mat. So your prediction should be cat and mat for these 2 particular tokens, correct? And your input is this sentence, which happens to be an S cross D matrix. S is the total number of words in your sequence, and D is the number of dimensions for each of those words or tokens, correct? Now, this will go through the attention layers of the transformer. It will go through all those multiple blocks of the encoder-only transformer. And then it produces a context-aware embedding matrix. It goes to the S cross D matrix here, and it produces a context-aware S cross D matrix here. Obviously, because the weights are all random, it just produces random junk right now, correct? Now that you have masked the second token and you have masked the second and sixth token. So what you want to do is for the second token and the sixth token, you want to predict, now what should this word be? But this is a S cross D matrix. Now, how do you make a prediction? Like this is slot 2 and this is slot 6. In slot 2, I want to go and predict, okay, I think the word should be cat and slot 6 should be mat, right? So which means that you need to take this matrix, and if you can project it into a matrix that is S cross V, so S cross D to S cross V, then what you have is for each of those slots, you have elements in this area, V slots in this area. What is V? V is the total number of words in your vocabulary, because any word that you're going to predict should be a word that is there in your vocabulary, correct? So if you can extend this from D dimensions to V dimensions, then all you can do is you can apply a softmax on this, and softmax will do what? It will pick that slot that has the highest probability, and that index becomes the word from your vocabulary that you will pull and say, I think it is this word. So that's what you're trying to do. So for this slot, you're going from D dimension 1 cross D to 1 cross V. Okay, and you're going to predict from there. You do the same for the other slot as well. So how do you take an S cross D matrix and project it into an S cross V matrix? It's pretty straightforward. You put in a feed forward neural network, right? What does a feed forward? You can use a linear layer or you can put a feed forward neural network. Okay, what does this do? Let's say the feed forward neural network has two layers. The first layer has D cross P, which P is some projection size, let us say. And when you take a S cross D and you multiply it with a D cross P, you would get an S cross P matrix, correct? Now, from S cross P, you need to get an S cross V because you're going to go, eventually your goal is to go from S cross D to S cross V, right? But you have an S cross P here. So how do you go from S cross P to S cross V? You'll need to have a P cross V as the second layer, because S cross P, which comes out from here, times P cross V will give you an S cross V, correct? So this is a very simple thing. All you're doing here is you're putting this feed forward neural network layer. So once you have this, I have taken my S cross D matrix and I have projected it into S cross V, and then I can use softmax and I can get the words out. All right. So let's say that the words it has predicted is dog and rug. Dog for the slot 2 and rug for slot 6. Clearly, that's wrong because the ground truth value says that you have actually masked cat for slot 2 and mat for slot 6, and your prediction is dog and rug. So what you would do is that you would use cross entropy loss, because you're using softmax here. Cross entropy loss between the words for the second slot, which is cat versus dog, and another cross entropy log for the sixth slot, which is mat versus rug. Okay, then you would average that and you would backpropagate that. So when you backpropagate, what are you doing? You're adjusting the weights in the feed-forward neural network head that you put here, as well as all the weights here. Okay, so you do this again and again and again and again till your loss starts to converge down to 0. So going back to the 4 components abstraction. So what are the 4 components here? For the input layer, what is the task here? You're doing pre-training, right? Where you're trying to teach the large language model the constructs of the human language. So the task specific input format would be what? You just take sentence as is and you mask certain number of words in it. Okay, and you also gather the words that you masked in your white true. The task specific training head that you're going to use is a feed forward neural network. It can also be a linear layer. You can choose either of them. Feed forward neural network gives you more weight, so it learns better. So you use a feed forward neural network as your task specific head here. Your output function is your softmax and your loss function is cross entropy loss. Okay, so that's all you do for doing pre-training. And the question is, what do you mask? Which tokens do you mask? So what the paper proposed, and that is something that's used consistently across other variants of this, is you mask about 15% of the tokens in each training sentence. So you get a training sentence, let's say it has 10 words in it. You mask randomly, you pick 15% of those 10, which is about 1.5. So let's say you round it up. So 2 tokens out of the 10 you would mask. Okay, randomly. Now, within the random tokens that you picked, what you'd also do is that 80% of the time you actually replace it with this mask token. 10% of the time you replace it with some random word from the vocabulary, and again 10% of the time you replace it with the same word. And the reason for that is you do not want the large language model to actually start learning mask also. That is why you kind of sometimes also give it the correct word. Okay. Now, one other question that comes up here is, why only 15? Okay, why don't I mask 80% of the words in a sentence, training sample, and make the neural network learn that? And the reason you don't do that is because, number one, if you mask too many words, you have lost the context that can be established by looking at the order in which these words appear. Remember that the whole idea behind self-attention and large language models is that you can extract the context that is flowing across words in your text paragraphs. So that is lost if you mask about 80%. So you cannot mask a lot because you want to retain the context, correct? Then you'll say, okay, that's fine. I understand why I cannot do more. But how about you do this thing? You start off with the sentence and you mask the first 2 words, feed it, again you give the same sentence, mask the next 2 words, and then give the same sentence, 2 words after that, and so on. So do it for everything. Why don't you do that? You could do that. But the problem with doing that is that it's going to take a very, very long time. Remember that pre-training is done by feeding all the sentences that you can get your hands on, pretty much the entire internet web crawl. We're talking about literally billions, if not trillions of sentences. So if you are passing the same sentence and then let's say 15% of those words are masked, and then with the same sentence another different set of 15% are masked, pretty much you want to touch all the words. It's going to take an enormous amount of time, and it's going to cost you a lot of money as well. So you really don't want to do it that way. You said you just give it sentences, randomly picks 15% of the words in the sentence, and then let it learn. And you just do this till your loss converges down to as close to zero as possible. Okay, that's what masked language model is. Now, let's just try to understand this from a different perspective, right? Which is, what is the interplay between self-attention and masking? So, for example, as a human, if I were to give you this sentence, she mask to her house. So mask is, I've hidden this word, right? And like it's a fill in the blanks kind of thing. So you can fill it up with anything. Like for example, you can say she drove to her house. Okay. But if I add more context, for example, if I say she got into her car and then she masked to her house, that you're going to actually substitute it with drove. You're not going to substitute it with ran to her house, right? Because you see that there's a car thing here, and car and drove go together. So self attention gives you that kind of a context that will tell you what this mask is going to carry. Now let's actually build this out. Let's say I do a few more formulations of this. So she got into her car and then the mask word becomes drove. But let's say she put on her shoes and then you would not predict drove. You would actually have to predict ran, right? She picked up her bike and then you're not going to say drove or ran. You would say cycled to her house. Or if you want to use suffix, you want to add to the end of the sentence. So let's say she masked, fill in the blank, to her house because she injured her foot. That this context tells you that it cannot be cycled, ran, or drove. It is going to be limped, and so on. So with self-attention and by masking, you will learn that the context will drive what word needs to be substituted. That's why in the past episode I told you, right, beneath the words that form text, I think there is a hidden geometry of thought, how words are connected to each other. It's like almost like a very intricate graph, and there are weights to those graphs and all that interconnectedness between words. So there's a hidden geometry of thought, and that the large language model is uncovering that geometry for us. Okay, all right. Now let's look at the other type of pre-training, which is called replace token detection. So this is an idea that was proposed in a paper in 2020, a paper called ELECTRA. So this comes out of Google as well as Stanford. And Electra uses a different strategy. And by the way, Electra, for a similar size model, it is much faster, about 4 times faster to train. It costs a quarter of what it would cost to train, let's say, using masked language model. And the beauty of Electra is that it actually learns from 100% of all the tokens in the sentence, rather than just 15% that what a masked language model uses. Okay, and it also improved the performance. It went from using the BERT's MLM based technique of pre-training. It went from on the glue score of 79.9 to, with Electra, it went to 84.7. It's a plus 4.8 points, which is a very significant boost in terms of performance. Okay, so how did they do this? So what they do is they use two encoder-only transformers. The first encoder-only transformer is called as a generator, and the second encoder-only transformer is called as a discriminator. The generator is a small BERT-style large language model where you would use masked language model. The discriminator uses a different strategy, which is called replace token detection. So let's walk through what really goes on behind the scenes in Electra. So what you would do is you'd give it a sentence. Let's say you pick a training sentence, a sentence from a training data set. The cat sat on the mat. Okay. Now the generator is using MLM, masked language model. So you're going to mask certain words. So let's say you mask cat and you mask mat. Okay. So your input to the generator is X is all the tokens with two of these tokens masked. Okay. And the white true value, ground truth value for the generator is cat and mat. What I have masked should actually be cat and mat. Now, this is using MLM. So I'm going to use a feed-forward neural network and use softmax, and then I would predict that the first masked word is going to be, let's say, dog, and the second masked word is going to be rug. I know it is incorrect. It's a wrong prediction, but that's fine because you're going to train it to fix it over time, right? So the generator's Y pred is dog and rug, whereas it actually should have been cat and mat. Now this is MLM. There's no difference between what you have seen in the past and before then and this. The one big difference is that this generator is actually a small encoder-only transformer. What is a small encoder-only transformer? Remember that in an encoder-only transformer, you have multiple encoder blocks, and you can decrease the total number of blocks so that you take out a lot of those weights and make it much smaller, much shallower in terms of the depth, right? You can also decrease the total number of dimensions, right, for each of those words. So total number of weights becomes smaller, so it's much faster. When the weights are more, it takes more time to compute. It takes more flops to compute. But if you decrease the total number of parameters, then it becomes a much smaller model. Architecturally, it is the same, but it's a much smaller model. So as a result, it is going to have a smaller footprint. Okay. Anyway, so now you have what this MLM-based generator does, predicted some words, which could be wrong, as we said. Now this becomes an input to the discriminator. Remember, we are still in the pre-training step. So in the pre-training step, you do not want to use human labeling. You want to do self-supervised learning. Okay. So what you do here is you take the output that is coming out from the generator and make that an input into the discriminator. Okay. And you already know that these are the words that you have masked. What is the correct values? And that dog and rug are not the correct values. So what you do in the discriminator is the input becomes whatever is coming out from the generator's output. But the ground truth value for the discriminator is you say, is the first word the original word or has it been replaced? Is the second word the original meaning original to the input, the training sample? Is the second word the original word or is it replaced? It is clearly replaced. These two are replaced. Is the third word the original word or is it replaced? It is not replaced. So you pass it as 1. The second word is replaced. You pass 0 here. So you do this, and what you would do is you put a feed-forward neural network ahead here, and that feed-forward neural network for each of the slots here, each of these tokens, it is supposed to predict whether that word has been replaced or it is the original. Okay, that's why you're going to have sigmoids that are coming out of this feed-forward neural network, unlike here, which is trying to predict words. This is only predicting whether, given this word, has it been replaced with some other word or it is there actually in the training data set. So your y true for the discriminator, the prediction, so this should actually have been predictor, y pred for the discriminator, let's say is 101101. So now you have this. What you do is that you would calculate the loss. Because it's using sigmoid here, you would use a binary cross entropy between the discriminator's y true and the discriminator's y pred. You would also calculate the loss separately for the generator, which is using cross entropy because using softmax here. Okay. Now, when you want to go and back propagate this loss, you actually go and back propagate this loss. Let's say this loss here, y loss discriminator. You go and back propagate, adjust the weights in this feed forward neural network, adjust the weights in this discriminator transformer, right? Do you go back and adjust this loss in the generator? You don't, because these two neural networks are not really connected from a neural network point of view. This first neural network is just generating text that becomes an input to the discriminator. So you just back propagate this loss only to this neural network arrangement here, and you back propagate this loss, the generators, only to this one. Okay. Now this is what ELECTRA has done, and it is called the replace token detection because it is trying to replace, it's trying to learn what tokens are replaced. Now when all of this is done and when the losses go down to 0, you throw away the generator and the weights that are there in the discriminator becomes your pre-trained large language model. Okay. Now what is the difference between the architecture of the generator encoder-only transformer and the discriminator encoder-only transformer? Architecturally, they are the same. It has the same word embeddings, positional encoding. It has the same multi-head attention. It has the same layer norm. It has the same feed-forward network. The only difference is the generator has a fewer number of such encoder blocks. The discriminator has a lot more encoder blocks. The generator has fewer number of weights. The discriminator has a lot more weights. Other than that, there's no difference between these two. What differs is this feed-forward, this head that you have here, right? This head here for discriminator is a feed-forward neural network that for each position, it will use a sigmoid to check if the token has been replaced or not. And the head here for the generator is again a feed-forward neural network, but only for the token, it will use a softmax to say that it has been replaced or not. Okay, this is RTD because it is now using and it's actually predicting whether tokens have been replaced, and all the tokens it is testing for. It has coverage over the entire words in your training data set, as opposed to only 15% of the words that is there in masked language model. Okay, and as a result of that, what they found out is that it is much faster for the loss to get converged than when you're using MLM, and it is also higher performing in the sense that it can give you a better GLU score. Okay. All right. So the third technique to do pre-training is called as next sentence prediction. Because so far in mass language model or RTD, all you have said is, okay, these set of word combinations make sense. This kind of word combinations do not make sense. Like, for example, you would not, things like she went there is correct, there went she is not correct. So you just figure out that kind of word formulation, right? But you also want to know, given two sentences, will the second sentence actually occur contextually following the first sentence or not? You also want to teach that, right, to this large language model. And that is done through what is called as NSP, which is next sentence prediction. So in that, what you do is that you would give it two sentences, always two sentences. Like, for example, you would say, she missed the last train as a first sentence. The second sentence is, so she walked back home. Is it possible that the second sentence could semantically follow the first sentence? If the answer is yes, then you'll say yes. It is a logical sentence to follow after the first. Let's say you would say she missed the last train, and then the second sentence you would give it roses are red. You would say, okay, no human would construct it like this, because those two sentences, one followed by the other, first sentence followed by the second, are not semantically next to each other, right? Like, other example would be, the intern deleted the prod database is the first sentence, and the second sentence were, we fired him immediately. It's a logical formulation. But if you say the intern deleted prod database and we promoted him to senior developer role, is the second sentence, is not a logical, semantically logical next sentence to follow, right? So that is what you want to teach BERT, or the encoder-only transformer. The way you do that is, you have to change now the input, because I told you the four things that you need to understand. The four things are, first is the task specific input. The way you do that is, this becomes a classification problem. Classification, why? Because you're trying to classify if the second sentence logically follows the first sentence or not. So what you do is that you take the sentence, let's say, my dog is cute, she likes to play. These are the two sentences. You tokenize it, and then the input arrangement will be, you add a special token called a classifier token. Okay. And then you add the first tokens of the first sentence. So my dog is cute. By the way, even the periods are added. It's a mistake not to put it here, but even things like periods, commas, everything is added as their own token. So first you put a special CLS, which is classification token. Then you add the tokens of the first sentence. Then you add a special token called a sep, which is a separator. Then you add tokens of the second sentence. Then you add again sep, which tells you the boundary between these two sentences. Okay. And your job is to figure out the head on this side here, the pre-training head here, so that it can classify. This classification will tell you whether the second sentence semantically follows the first sentence or not. That is all you're trying to do, right? So the way you would do that is, you would only focus on this CLS token, and you would project it using a feed-forward neural network that will predict whether, binary prediction, is the second sentence logically following the first sentence or not. That's what is next or not is next. That's what you're trying to predict. So you could use a sigmoid. Typically, you see that softmax is used because they have optimized the implementation of softmax, and they say, listen, a softmax over a feed-forward neural network that has just two elements in the last layer is the same as just having a sigmoid over one element, right? So they use softmax just to make everything consistent. So you do a softmax, and it'll on two slots, and it'll say, what is this next? Then it's pick the first slot, and if it picks that first slot, the second sentence logically follows the first one. It picks the second slot, it means that it does not. And this one you'll again repeat again and again and again across multiple sentences, and it will learn how humans determine what sentences should follow each other or not. Okay, that is next sentence prediction. Now, there's a fourth technique called sentence order prediction. So, sentence order prediction is almost establishing a cause and effect kind of a relationship between sentences. So, for example, if the sentences are ordered this way, she unlocked the front door, and the second sentence is, then she entered the house, so that they are ordered in the correct way. For example, if I were to just swap the order and say, then she entered the house, followed by she unlocked the front door, so that they are swapped and they are not logically following each other. Not semantically, but like a cause and effect in a time sense way you're trying to determine. NSP is saying, okay, do humans determine that the second sentence can actually occur after the first? Sentence order prediction is, can the second thing happen, or rather, can the first thing happen followed by the second thing, or can the second thing happen followed by the first thing. That is what you're trying to determine. For example, he made coffee and he drank it is a correct order. But if you were to give a sentence like he drank it and followed by he made coffee, that ordering is not correct. Okay. So how do you train this? Again, it's pretty straightforward. Exact same thing like you would do next sentence prediction. You would have a CLS token. You would pass in all the tokens of the first sentence, followed by a separator special token, followed by all the tokens of the second sentence, followed by a separator special token again. You would go process it through the encoder-only transformer, and then from the first token, which is the special CLS classification token, you project it using a feed-forward neural network, and then you pass it through two neurons at the last layer, and then you would use a softmax and say, okay, is this ordered or is it swapped? Okay, and based on that, you would propagate the loss back and adjust the weights, and so that it will start to figure out that this ordering of sentences is correct or not. Again, completely can be done in self-supervised manner. Yeah. So now pre-training is done. Once you've gone through all these steps, pre-training is done. At this point, what is it that the large language model has learned? First thing it has learned is contextual word representations of sentences, which means going back to a very first example, he entered the Apple store eating an apple. It knows that the first apple means more of a company and less of a fruit. The second apple is more of a fruit and less of a company, and so on. And it knows how to adjust those weights of individual dimensions so that it can swing the first word's apple's feature dimensions on company more and less on fruit, and vice versa for the second one. So what contextual word representation means is it has learned that the word bat means something different when it's used in the context of baseball versus when it's used in the context of cave. That's the first thing it has learned. Second thing is it has also learned word to context mapping. Like, for example, hey, put that over there. What that and there means, right? So that is also something that it has learned. It has also learned syntactical and grammatical relationships. For example, it has learned he ate this apple is correct, whereas Apple ate this he is not correct. Okay. And other one is it figures out, it learns that word co-occurrence and plausibility. For example, eating an apple makes sense, but eating a laptop doesn't. Okay. And finally, it has also figured out sentence level semantics, right? Which is you'd say things like she unlocked the door and then she entered the room, or he made coffee and then she drank it is correct, whereas yeah, he drank it and then followed by he made coffee is not correct. Okay, this is what we have taught the encoder-only large language model. It has learned language at this stage. So just like you have different types of decoder-only models, like DeepSeek and GPT and Llama and so on. Similar to that, even encoder-only transformers, they have different types of encoder-only transformers. BERT is one of them. There are variants of BERT called Roberta, Albert, Distilbert, and so on. And then you have things like Electra, which is more of a modern type of a encoder-only transformer. And I give you a chart here and I tell you among those four training strategies, pre-training strategies, which of those large language models uses which one. For example, BERT, which is the most popular, most commonly used in production today. It uses masked language model as well as next sentence prediction. Roberta, which is the BERT model, but it says what if I can increase the training data set, I really do not even need to do next sentence prediction. I can just do masked language model and I can make a transformer learn the different constructs of a language. Just as by comparison, if you look at it, Roberta's training corpus is significantly larger than what is used to train BERT. Even the total number of words that Roberta sees is actually more, 50,000 unique words it has seen in its training data set versus what BERT sees, which is 30,000, right? Electra, for example, uses masked language model in the generator part of the transformer. It uses the replace token detection in the discriminator part of the pre-training phase. It does not use NSP or sentence order prediction. Albert, for example, uses masked language model. It does not use NSP, instead uses SOP. Anyway, you can see this table and you see that there are different encoder-only large language models that you can pick from. And I'm also giving you the open source or open weight models that you can download from the internet, from Hugging Face, for example. These are the names of those models. And this is the year in which it was developed and the company that developed it. And this is the total vocabulary size in this pre-trained data set. Okay. So at this stage, we are done with pre-training. Now let's move on to the step 2, which is fine-tuning. So now we have a large language model that understands language and sentence construction. Now we want to train that take that learning of language and train it to perform tasks. Tasks could be things like, as I said, classification or labeling or named entity recognition, similarity or duplicate detection, and so on. Okay. Now let's start looking at the different types of tasks for which you can fine tune our large language model. The first task I'm going to show you is classification. Okay. In classification, what you want to do is, let's say that your use case is to take movie reviews and classify them into, is it positive or is it negative? Okay. So it's a multi-class classification problem. So is that review positive or is it negative? So the way you would build that is you would take your pre-trained encoder-only large language model. Then you would take this training sample. Remember that in fine-tuning, you have to have labeled data. So you already prepared your training data set for fine-tuning with movie reviews and the corresponding classification of positive or negative. So I'm going to take the first sample. Let's say it says absolutely a masterpiece. I'd watch it again anytime. I would tokenize it. And then what I do here is I would assign this special CLS token for classification. I'll send it through my transformer and it will produce a context-aware embedding matrix. And now, because it's a classification problem, I will send it through a feed-forward neural network with two logits at the end. First logit will, let's say, signify whether it is positive. Second logit will signify whether it's negative. And because it's a multi-class classification problem, what is the output function I'll use? I'll use a softmax output function. So because I have two logits and I softmax it, one of these slots is picked. If the first slot is picked, which is the 0th slot, it is a positive review. If the second slot is picked, which is the index of 1, then it is going to be the negative review. Okay. Now, given enough such training samples, it is learning what set of words and what kind of sentence constructions are leaning more towards a positive sentiment or classification of the movie review and which ones are leaning more towards negative. So you do this, and because you're using softmax as your output function, your corresponding loss function is going to be cross entropy loss function. You then back propagate the loss back where this FFN's weights are adjusted. Then this pre-trained LLM's weights are also adjusted, and over time the loss converges down to 0, and now you have a fine-tuned large language model, and this is the one that you will save. Okay, and you can use this for doing production classification of movie sentiment reviews. Okay, all right. So the second one I would show you is, second task is going to be labeling. So in labeling, what you want to do is that, let's say you're trying to build a support portal, and in the support portal a user has reported an issue, and you would like to train your language model to automatically classify the issue into whether it is a billing issue, is it a software issue, is it a hardware issue, is it a combination of both, and so on. So one or more or zero or more such labels can be assigned to each incoming issue. Okay. So how would you go and build that? It's actually, it mimics the similar strategy that we studied so far. You pass in an issue during fine tuning, you tokenize it, and then you attach this special CLS or the classification token at the beginning. You send that input to your pre-trained encoder-only large language model that will produce you a context-aware embedding matrix. Then you send the CLS token part of that, just that row, into your feed-forward neural network, right? And that feed-forward neural network, that head, that task-specific head, has three logits in the end. Why three logits? Because there are three potential possible labels that you could assign to each of these issues, right? And because zero or more such issues can be assigned, you're going to use sigmoid as my output function. Remember that a sigmoid squashes a value between 0 and 1. I can use a thresholding function on top and say incoming logit value, whatever it is, if it is greater than, once I pass it through sigmoid, it is greater than the threshold, then I'm going to select that label applies to this incoming issue. Okay. Because I'm using sigmoid, my loss function becomes a binary cross entropy loss function. Now, once you have gone through this thing through multiple training samples and back propagating the loss, fixing the weights in this feed forward neural network head, as well as this already pre-trained LLM, and the loss converges down to near zero, I now can save my fine-tuned large language model, and I can use this for doing labeling of issues that are coming in. Okay. What if you want to build one single large language model that can in one shot perform multiple tasks? For example, two tasks. Task one is classification and task two is labeling. Can we build one large language model that can perform both these tasks simultaneously? We can, and I'll show you how we do that. Okay. So let's say that my task here is to look at issues reported by either a customer or your QA. And just as an example, I'm going to take Kubernetes log messages as my data, right? And these are the different issues, like, for example, pods in production namespace are stuck in crash loop backoff. What you want to do is, given this text, you would like to train your large language model to classify the text as whether it's urgent or not. Is it urgent or is it normal, right? And you also wanted to automatically label using zero or more labels which category this particular issue belongs to. Like, for example, the first one belongs to this category of pod, the second one belongs to this category of PVC. So I'm going to label it with PVC. The third one belongs to a category of both stateful sets as well as pods. I'm going to give it both those labels. The last one, you can label it with stateful sets, pods, and networking, and so on. Okay. So this is what I would like to build my large language model for. Okay, very quickly identify whether an issue that is incoming is urgent and classify it. What might you actually use something like this for? You might actually use this for doing automatic triage. You can use this for doing automatic allocation of different issues to different engineers and bring in the right experts to go look at these issues very quickly and all that. You can automate all of that stuff. Okay. And you can also use this to generate very good reports in the future. All right. So how do you go about building a large language model for this? So what you do to fine tune your large language model to do multitask classification is you take the incoming issue text as your input, tokenize it, and then you, for the input formatting, you would essentially put a CLS token in the front, which is again a classification token. You'd send it through your encoder-only transformer that produces context-aware embedding matrix. Now, for the head that you put on top, you're doing two tasks, right? So you need to have two different heads. The first head will focus on classifying the incoming text into whether it is urgent or normal. Okay. So it is basically a multi-class classification problem of which it can pick either one of these two classes. Is it urgent or is it normal? So you're going to have two logits at the end of that FFN, the feed forward neural network. And the first, the first logit, if it's picked, then it's going to be an urgent issue. The second logit, if the logit is picked, then it's going to be a normal issue. If you have two logits and you want to pick one of them, you would use softmax as your output function. And because you're using softmax, your loss function is going to be cross entropy loss function. Now, for the second task that you would like to do simultaneously is you would like to label the incoming issue into zero or more of labels that you already predetermined. Okay. So for all the labels that are unique labels that is there in your training data set, you would have those many number of logits at the end of your second feed forward neural network, which is basically the second head. And because you're doing multi-label classification, remember, you're not just picking one label out of the, let's say there are 20 different possible labels. You're saying that multiple labels could apply to an incoming issue. So you're doing multi-label classification. Because you're doing multi-label classification, what would you use as your output function? Sigmoid. And then you would say if the sigmoid, remember, a sigmoid function will return a value between 0 and 1, regardless of how small and how big the actual value is, right? You essentially send any value, a negative value, positive value, small value, large value, doesn't matter. You send it through a sigmoid function, it will always squash that value between 0 and 1. Because it does that, you could treat it as a probability, right? And you say that if the sigmoid value that is being outputted is basically greater than a certain threshold, let's say the threshold is set up that you select as 0.75, then you say, okay, I'm going to say that, okay, this label applies to this particular incoming text. Okay. So for your second head, which is a feed forward neural network to a different feed forward neural network than the first head here, the output function is sigmoid. And because you're using sigmoid as your output function, you're going to use the binary cross entropy loss function. All right. Now let's see how you would implement this. Now what I've done is I've basically structured my implementation so that you can actually, in your mind, build a mental model of how you solve problems like this. So the mental model of solving problems like this is to basically divide it into three phases or three parts or three steps. Step one is that you would like to, which you can see here, I'm summarizing it here. Step one is you would like to build a custom model because you already have a pre-trained large language model that understands, let's say, the English language, correct? Let's say it's BERT, I can download it from Hugging Face, which I do in the first function here, download pre-trained encoder-only model. Now, this model now needs to be fine-tuned so that it can classify Kubernetes issues because when the model was pre-trained, it does not really see any of these issues, right? Now I'm fine-tuning it because it understands language. It's a great starting candidate to be fine-tuned so that it can classify incoming Kubernetes issues. So what I do is in my first step is I also build this classification and labeling model that extends the pre-trained large language model. The next step is, okay, now that I have my model, I'm going to prepare my training data set for fine tuning. Remember that in pre-training, everything is unsupervised. But in fine tuning, you have to label because you're doing supervised fine tuning or supervised training. So, which means that I need to have a collection of Kubernetes issues, and each of those issues then individually has to be classified into whether it's urgent or normal. And it also has to be given some labels, right? Zero or more labels. So, I have to prepare that training data, fine tuning training data set. I do that in this function called prepare data set for fine tuning. Then once I have that, I need to now go through each sample in the training set and I need to fine tune my classification and labeling model for a certain number of epochs. Once it's done and the loss converges down to near zero, I'm going to save this fine tuned model, classification and labeling model. Now I can take this model and then I can move it to my production servers or what have you, and then I can get into my step three where I'm going to be inferring from that model. In that inferring step, what do I need to do? I need to first load this model. It's already trained, and then I need to just give it some text or text of issue that's coming in, right? And define a function called classify and label support issues. And what this does is it takes text and then it will give it a classification of whether that incoming text of that issue is urgent or normal, and it will also assign zero or more labels. Okay. So this is the general structuring. And I think generally when you look at problems like this, I think this three-step way of structuring your code or your general process of fine tuning and then inferring makes a lot of sense. So I've actually built the rest of the demos in this episode also using the same structure. All right. So I've implemented a Google Colab notebook to demonstrate how you would build your own custom model to do multi-class classification and labeling as well as actually do the inferencing. Okay. So what I do here is I'm going to install the required Hugging Face transformer libraries. I've already installed it, so I'm not going to run that again. Next, what I'm going to do is I'm going to import my libraries since I've installed it. So I'm importing them. This is the Hugging Face transformer library. This is PyTorch and so on. Okay, scikit-learn and all that. Okay, I've done that. All right. The next one is I'm going to load my data set. I need a place where I can store my data set. I need to download the pre-trained transformer and all that. Because I'm using Google Colab, I'm going to do that in Google Drive. I'm going to put this in this subfolder called CIDL. Okay, this CIDL subfolder, and I'll store my models here. I'll store my pre-trained model in this subdirectory. I'll store my fine-tuned model in this subdirectory. I'll store my data sets in this directory and so on. Okay. All right. So let me run this. As you can see, the dataset directory is going to be here, and my pre-trained model will be under models pre-trained. My fine-tuned will be under models fine-tuned. Okay. Now, the model that I'm going to download is BERT based uncased. Okay, this is basically a pre-trained large language model, encoder-only large language model. All right, so that's that. Now let's go here. Now let's look at this code here, which is building our own classification and labeling model. I'm going to download these pre-trained models first. That's going to happen here. All right. So once that is done, while that is happening, let's look at the implementation. So this is the classification and the multitask model, right? So what I do here is to this class, classification and labeling model, I pass the model name. Model name is what? BERT base uncased. This is the model that I'm using, the pre-trained model, correct? All right. Now I'm also going to pass it the labels. Remember that there are so many different Kubernetes specific labels, right? Because I'm doing this for Kubernetes specific issues, correct? Actually, let me show you the training data set once. So the training data set I have is a CSV file where there are three columns. The first column is the Kubernetes issue, which is in text form. Then the second column is the urgency classifier, which will classify any issue as normal or urgent. And the third issue is an array of different labels that I'm pre-training my transformer for, that I should apply to this kind of issue that I see here. All right. So when you see labels here, it's basically all the unique labels that are there in this third column. Okay, the total number, because I need to create those many number of output logics, right? All right. Anyway, so this comes in here, the model and all this stuff. All right. Now what I do is that I get the base model is going to be what? The base model is going to be the pre-trained LLM, right? So I'm going to get the pre-trained LLM. I've already downloaded it here, so I'm pulling it from the cache. All right. And next, what I do is that I need to attach two heads, right? The first head This is going to be the agency or / normal classification, right? The second head is going to be the multi-label head, right? Multi-label head. Okay. Now, both of them are feed-forward neural networks. There are two layers here. It could also be, as I said in the past, it could just be one single linear layer. That's also fine. I typically like to use FFNs because that gives you more learning capabilities, more weights, and so on. Okay. Now, what is hidden size? Hidden size is, first of all, this Hugging Face transformer, the pre-trained transformer, was trained with the sequence length of S, right? It's typically 512, and it was also trained on a certain number of dimensions, right, which we call as D. I think it is 768 or something like that. I believe some 768 or something. Okay. So the input array is going to be an S cross D matrix, right? This is what is going to come in. So this hidden size is basically this D. Okay. All right. So how am I sizing my feed-forward neural networks? I'm saying that the first layer here has D cross D matrix as a matrix, and it goes through a ReLU activation function here. And the last one is it has a D cross. Sorry, it has a D cross 2 size matrix here. Why 2? Because this classification is, I'm trying to classify, it's a multi-class classification with just two classes, urgent or normal. Okay. This, by the way, because I'm using multi-class classification, I'm going to use the cross entropy loss function. Because I'm using cross entropy loss function, I know that my output function is going to be a softmax function, correct? All right, for the second head, I'm going to use, first layer is going to have again a D cross D, which is this. It's going to pass through ReLU. Then the last layer is going to have okay, how much is it going to have? It is going to have D cross L, right? What is L? L is basically the total number of labels, the unique labels that you would like to classify your incoming text into. And I'm saying that the loss function I'll use for the second head is going to be a binary cross entropy loss function, which essentially means I'm going to be using sigmoid here, correct? As my output function. That's what it means. All right. Now I've set up my custom model. Now I need to show you also how the forward pass works, right? Forward pass, remember in PyTorch is when you're training, the forward pass is called to give you a training input, right? And also the labels, right? And then you're supposed to run it through your neural network. So let's understand this a little bit better. What really gets into this function during training phase? Okay, the training phase. Okay, let's say the text was something like pod. So the text is okay, pod is sitting in a crash loop or something like that. Okay, something like that. Let's say now this gets of course tokenized into something like pod is sitting in a crash loop, right? So what it's going to get tokenized into. But neural networks do not understand text. So the tokenizer actually gives you input IDs, right? Input IDs. So input IDs, what are those input IDs? Input IDs are, by the way, when you tokenize, remember that because you're doing this fine tuning, it's a classification fine tuning task. You also need to have this special CLS token. Right, so there's going to be a CLS token added at the front. So when you get the input IDs, which is basically the input that's coming into your forward method, you will get the CLS token ID, a special ID that the tokenizer is assigned for CLS. Let's say the ID is 1 as an example, okay? Then the ID for pod, okay? And by the way, there could also be padding tokens. Let's say pad and pad, okay? So next that you get is the padding, next is the token ID for pod. Let's say the token ID for pod is 23, the token ID for which is here is, let's say, 45, and the token ID for sitting is, let's say, 67, right? And the token ID for in after that is, let's say, 99. Token ID for A is, let's say, 3. The token ID for crash loop is, let's say, 17. Now you have pad, right? So let's say pad tokens are 100 and 100. Okay, that's it in your tokenizing database, right? Vocabulary. So this is what your input is going to be. It's all going to be numbers, token IDs, correct? Now, you do not want the large language model, the transformer, in the attention layer, right, self-attention layer, to calculate the attention on pad tokens. Why? Because again, your BERT pre-trained model was trained on a maximum sequence length of 512 tokens, correct? And your incoming sentences could be much, much shorter, which means that you would have a lot of pad tokens. And you do not want your attention module to basically focus on those pad tokens, which means that you need to mask them out, right? That is where you notice that this thing called attention mask is passed, right? And what the attention mask does is basically it looks like this. Attention mask is, this is how it's going to be structured. It says do not pay attention to the CLS token, Okay, so it's going to be 0. Pay attention to this valid token called pod. Pay attention to this valid token called is, to sitting, to in, a, and loop. And do not pay attention to pad and pad. So they'll be 0. So valid tokens get a value of 1 in this attention mask array, and the special tokens get a attention mask value of 0, so that they do not get computed. They not influence the calculation of self-attention. That's all that happens here. Now, once you have this, you would basically take this and you will pass it through a base model. Again, what is the base model? The base model is the pre-trained LLM that you have downloaded from Hugging Face. BERT base and case is what I have, right? Now, once you pass it through this, it will go through the embedding layer, the positional encoding layer, self-attention module, layer normalization, feed-forward layers, all of that stuff, right? It goes through all of those things across multiple blocks, and it produces this output. What is this output? The output is basically nothing but a S cross D size matrix, right? S is a sequence length, and D is a total number of dimensions. This is a context-aware embedding matrix for this incoming sentence, right? Now, I'm only interested in the CLS token part. The CLS token is basically what I'm using to classify, right? On which I'm essentially attaching my two heads, correct? So I basically get the first row from this. How many rows are there? There are S rows, right? So I'm only going to get the first row, which is the CLS token. That's what I'm going to get. Okay, so this CLS token, okay, let's just go with this. So CLS token is what? CLS token, this is going to be 1 cross D. Y1 is only one row, right? But it has D dimensions. Now I pass this one, that row, through my urgency classifier. Okay, when I go through my urgency classifier, it goes through this one here. It basically goes through this one. It goes through this linear layer. Now, actually, let's do the computation here. This is the first urgency classifier FFN, right? So what goes in there? It basically 1 cross D goes in. Okay, and it gets multiplied with the first layer of my urgency classifier, which is this, which is size D cross D. So that's going to be D cross D. So it will produce what? It will produce 1 cross D size matrix. That goes through a ReLU, correct? Which gives you non-linearity, which is good, ReLU. And now ReLU will also produce again a 1 cross D matrix, right? Now that gets multiplied with the second layer here, right? The second layer is what? D cross 2. Why 2? Only two classes, right? Urgent or normal. So D cross 2. So what comes out of here is what? What comes out of here is a 1 cross 2 size matrix. Okay. So it is either, if it is 0, then it is going to be urgent issue. And if it is 1, it is going to be a normal issue. That's what it means, right? 2 slots, right? And that's what it means. Okay, actually it is correct. This is what it is. 2 slots, and this is what it is. So run it through the urgency classifier. Now let's look at what happens to the second one. Now you pass the same output, the output from the CLS token, to my second FFN, which is my multi-label labeler, right? Which is the second FFN, FFN2. Now this one is also going to get this 1 cross D. Again, why 1 cross D? I'm only interested in the CLS token here. That's what I'm passing, correct? And then you multiply it with the first layer of my FFN there, which is again a T cross D, right? It's a different feed-forward neural network. They are not sharing the same way. It's a different feed-forward neural network, right? Now that becomes a 1 cross D matrix. Now that you pass through ReLU, right? ReLU, and that goes through, is this here. And that goes to the next layer, which is, by the way, the ReLU again produces 1 cross D. And this is going to be, the second layer has how many? It has D cross, total number of labels here. Let's say L labels are there, right? D cross L, so which will produce a 1 cross L size matrix. And L is the total number of labels, so you can essentially use sigmoid on that to get your which labels you would like to allocate, okay? Or which labels are going to be predicted for this incoming text. Now, the same forward method is called both during training as well as inferencing. And the way you would distinguish between the two is during training, you would also get the Y true, right, for the individual like urgency labels as well as the multi-label thing, right? So, for example, this is the Y true for the first classifier, which is the urgency classifier, and this is the Y true for the multi-label classifier, correct? So you need to compute, because you're training here, you need to compute the loss. So the loss you would compute as, for the first one, you would say, what is this? Urgency logits. Urgency logits is, this is the Y pred, right? This is the Y pred of the urgency classifier, correct? Or the multi-label logits which you see next is basically the Y pred that's coming out from the multi-label labeler, right? That's what you want to get. So coming back to this, what is the urgency loss function? You already defined your urgency loss function as cross entropy, and to which you are passing the predict value from the urgency classifier FFN, and you're passing the ground truth value that you're getting from the training sample, which is passed in through this function. For the second FFN, which is a multi-labeler, the loss function is a BCE loss function, which is a binary cross entropy loss function. So the Y pred is going to be this value here. Okay. The Y true for that would be the ground truth values that are coming in from the training sample, which is all the labels that apply to this. Okay. Then I add up these two losses and I pass that loss back to the rest of the code, okay? So that it can do the back propagation and all that. And you don't have to manually do it. PyTorch is automatically going to do the back propagation when you do the training run. But I told you that the same forward function is used both for inferencing as well as training as well as in inferencing. In inferencing, obviously, you don't have the ground truth value. All you have is basically the input text, right? So which means that this is going to be none. So you go here, there is no loss, but you want to pass the predicted logit values from both the first FFN, which is the urgency classifier, as well as the second FFN, which is basically the multi-labeler. Why do you need this for inference? Because when you give it a text, you want to get back the classification, you want to get back the labels, right? That's why what the forward function needs to return is, in addition to loss, which is going to be whatever it is computed here for the training, it also returns the logits from the two FFN heads that you have defined. Okay. In the case of inferencing, the loss is going to be none, but you're interested in the outputs logits from the two FFN heads. I actually extend this method by having this thing called save pre-trained, which will basically save after I'm done with the fine tuning. I'll save both the base model, which is the pre-trained LLM, whose weights have now been fine tuned, right, based on this task, as well as the weights in my urgency classifier head and the multi-labeler head. Okay, everything I'm going to store. I'm also going to store some configuration information as to what model I use to fine tune and all of those. What are the labels that are there in this training sample that I use to train and all that. Okay, and this method will essentially load up a previously saved model. Okay, let me run this code. Okay, this is just compiling the code. Okay, now let's go down and see this. Let's see the fine tuning steps. In the fine tuning step, I need to prepare my data set for fine tuning. Okay. So preparing the data set for fine tuning is pretty straightforward. As I told you, right, I have the CSV file, which is the Kubernetes issues. I just check for, okay, do they have the three required columns that I'm interested in? Does it have the issue text itself? Does it have the urgency classifier? And does it have the labels? If it does not, I throw an error that there's a missing column. Otherwise, I convert everything to lowercase. The urgency labels are given to me as a array, right, of strings here. So I convert that into a Python string array, right? And then I use this multi-labeler binarizer method. All it does is that it basically gives me this, it takes care of looking at, if you go to this column here, it takes care of looking at all the unique labels that are there across all the issues in my training data set, and it'll assign a number to each of them, and then it'll use that to give me a numeric representation of which labels are there for each sample and which ones are not. Okay, because again, neural networks only understand numbers. I need that. So this is a nifty way of doing that. Okay, all right, so I do that and then I pass it through my tokenizer. So what is this tokenizer? This tokenizer is basically the same tokenizer that was used during the pre-training phase of my large language model, and this is key. You have to use the same tokenizer because that tokenizer is the one that has tokenized the text to essentially get the IDs and the breakpoints for the subwords and all of that stuff while building the pre-trained LLM, correct? You want to use that and you want to extend that same tokenizer. You want to use the same tokenizer because you want to get the same IDs back and all that, right? But you also want to extend it with the new tokens or the new things that are not there in that vocabulary. Like the Kubernetes issues might not be there. Kubernetes related tokens might not be there in the pre-trained vocabulary, right? So I want to extend it. Anyway, so I use the same tokenizer and it returns the PyTorch tensors, which is basically an array of the numeric IDs that are going to be passed to my forward method. Then Hugging Face expects this to be formatted in a certain way. So I use the dataset library from Hugging Face and I basically format it in this way, saying that my input that I'm going to give to my transformer now is the input IDs, which is basically what the tokenizer has gone through all the tokens, all the issues in my training data set and tokenize them, right? That one. the corresponding attention mask, the corresponding labels for each of those issues, and the corresponding urgency labels as well as the multi-label IDs. Okay. All right, so that's what it is. And then am saying that I'm going to split my entire data into 90% into training and 10% I'll use for validation. All right. So that's what this is. Actually, if you notice, and this has about 50,000 entries, training samples, and I'm splitting it into 90%, which is 45,018 for training and 5,000 for validation. It has 30 unique labels like API server related issue, auth related issue, config map related issue, configuration related issue, and so on. Okay. So 30 different labels potentially could be added to each of those issues. Okay. Now, next is I'm going to build. I'm in this stage, right? I'm going to basically build and fine tune my model. Building is nothing but, okay, let's just go back. So there's build and then there is fine tune. Okay. So let's just look at both those functions. Okay. Building is nothing but I'm just going to call this method and I'm going to instantiate in this particular thing. Okay. This one that you saw here. We already inspected this code. Let's not go into that again. And then fine tuning is what? Fine tuning is I'm going to give it the training data set. I'm going to give it the validation data set. And I also say how many epochs I would like to run this training fine tuning task for. I set up the training parameters. I'll not go into the details here. This is pretty straightforward. You can just look it up online. It will tell you what they are. Basically, it tells you where to save the checkpoint and what is the evaluation strategy and all that stuff. You can just look it up offline. It's fine. Right. Then I pass it through the trainer. I give it my model, which is the model is basically this one here. I will give it the training arguments, which is this one here. Then I'll give it my training data set, I'll give it my validation data set, and I give it this collate function. What is this collate function? The collate function is basically the Hugging Face transformer only expects text to come in, correct? It only expects the input IDs and the attention masks, right? It does not know that the way when they designed it, they did not know what is it that you're going to be fine tuning for. So you should also, and your fine tuning heads requires this urgency classifier, the labels urgent or normal as ground truth values. They also need to know the labels that are associated with each text, right? So how do you pass that? You use this collate function to basically go and pass those things also to your model, right? This model you want to pass. So that's the only function for this collate thing. Anyway, after that, I just do train and then it does the training. I am not going to run that thing because I've already run the training here. So I'm not going to run this again. We'll actually skip this part. I'm going to actually load a pre-trained thing just to save time. So this is I'm here now, this part. I've already trained it. What I'm going to do is I'm going to load it. Okay. So let's actually do load classification and labeling model. Let's actually look at this function first. Where is it? Okay, here. Okay, here. What it does is it basically instantiates this classification and label model from pre-train, which means that I'm going to give it the fine-tuned model directory. Actually, let me go back and show you this. So my models are stored here. This is my fine-tuned subdirectory. This is the classification and labeling task. So for this one, this is the data set that I had used. Okay, this is where my models are saved. Okay, so this is what I'm going to use. Like for example, this is my model. It is about 420 megabytes. And these are my different classification heads and all that is here. Right. Anyway, so I'm going to load that up. I'm also going to be loading my tokenizer, which is coming from this stuff here, because I'm going to be using the same tokenizer to tokenize the text for inferencing, right? That's all I do here. And then after that, I'll be calling the classify and label support issues, which will take the same tokenizer. It will take the same model. Since we are here, let's also look at the classify and label support issue that we'll be calling next, in which you pass the tokenizer, you pass the model, your fine-tuned model, and you pass it some sentence. And I'll come to this label names shortly. Pass it some sentence. That sentence is first tokenized, and then you would pass it through your model, and the model will give you outputs. From that output, you're interested in the urgency logits. You'll get the urgency logits. It's a multi-class classification head that you put, right? So you're going to use softmax and you're going to use an argmax on top, and it'll tell you, it'll give you which slot it selected. It can only select between a 0 and 1 slot, right? Essentially, it's going to give you that. And you'll also, from the second head, which is the multi-labeler logits, you'll get that and you'll run it through sigmoid function here because that was a multi-label classification head, right? And then it'll give you all these labels. Now, this is going to give you only integer. Anything is going to, neural networks only give you numbers, right? You're going to get these numbers. So you need to convert those numbers. Let's say it gives you that, okay, I should apply label 3, 6, and 9. What does label 3, 6, and 9 mean? I want to give it textual information. So you essentially give a dictionary of all the labels that you have seen during pre-training. and say, okay, 3 means maybe PVC issue, 6 means maybe it's a pod issue, and so on. So it just does the conversion into textual numbers, and then it returns both the urgency value in text and the label values also in text. Okay, now let's go down here and run this. So for running it, I have a set of issues that I have identified here. And you actually see this also because I have done this across two different types of data sets. One is Linux system logs and one is Kubernetes logs. Since I'm using Kubernetes based issues for this pre-training, fine-tuning task, I'm going to just focus on this. Just focus on this one. Yeah. Okay. So let's run that. It's loading my module and let it finish loading. Okay. It's loaded my module from this. All right. And then I'm going to go one issue at a time. I'm going to pass through a classify and label support issue, and it's going to give me whether it's urgent or not and the labels that it has deemed to assign to each of these issues. Okay, so let's run that. So it basically says, okay, let's see, back off restarting failed container. It is an urgent issue and it is in the domain of node health, pod and resource issues. Crash loop back off container failed to start repeatedly. It's an urgent issue and it is in the realm of, again, these things. Let's look at something that's not urgent. Let's say we'll go for something that's normal. Okay, here, container app terminated with exit code 137. Yeah, containers can stop for various different reasons. It does not have to be urgent. So it says it's a normal issue and it is assigning the labels of pod and resource issues and so on, right? As you can see, in milliseconds, it's basically able to classify any issue into whether it's urgent or not and also assign labels. Now you can build a lot of compelling end user applications with something like this. Like I said, right, it could be used to very quickly assign priorities to incoming issues. It can be used to go and assign a particular issue to one or two support engineers or development engineers and so on. It can be used to run reports, which issues are having a lot of, which type of class of problems is having more issues than the others. Like you can do a grouping by all these labels and then can you can do all those things. So you can build a compelling set of applications with something like this. All right. So that's our first demo. The third use case we'll explore is what is called as named entity recognition. So in NER, when you're given a block of text, something like this that you see on the screen, our goal is to extract the different entities. Entities are things like names of people. It could be things like the names of cities or locations or places, or it could be the country name, phone numbers, email addresses, what have you. So different types of entities. You define what are the entities that are of interest to you for the use case that you're trying to solve. Like for example, if you're trying to build a knowledge base application, then what you would like to do is that you would like to upload knowledge base articles, let's say PDF articles and all that, and you would like to extract the names of different things, whether it is product names or whether it is technology names or authors and whatnot, and then you would like to index that. So you would define for that, those are the different types of entity that you're interested in. If you're trying to build something for a customer service support desk use case, then you might like to extract entities like customer name, the product name, the subcategory of the type of issue, and all those things. So there are different type of entities that you could extract. Now, obviously, the question is, how do you make a machine or a neural network understand this? Traditionally, the way this kind of problem was solved is to use regexes, and you would define a variety of different regexes. Let's say a regex for identifying phone numbers, a regex for identifying credit card numbers, website URLs, emails, and so on. But it is very cumbersome because two things. Number one is sometimes the format in which that entity is recorded could be different. Phone numbers is a classic example, right? Based on different countries, the way the phone number is recorded is very different. And even within the same country, let's say it's United States, some people use parentheses to denote the area code, some people do not, some people use white space to denote the different components of a phone number, some people use hyphens. So it can all change. And writing all those regexes is very cumbersome, very painful, and error prone too. The second issue with regexes is if you're given a block of text and you're interested in extracting, let's say, 5 different types of entity, like names of people, phone numbers, credit card numbers, and their email address, and so on, you would write, let's say, 5 or 6 different regexes, and you have to run each of those regex against that block of text those many number of times. So you're serializing it, and there's no concurrent way in which you can extract all the entities with one pass over the text block. So regex is clearly, while it was one way of solving this problem, that's how it was solved in the past. Now that we are in this world of large language models, can we actually make the neural network understand the constructs of language and then just figure out a way to extract all these entities. So that's how we're going to do this now, okay? And I'll show you how to do that using an encoder-only transformer. So remember that we are fine-tuning the large language model. In fine-tuning, you need to first label the data so that the transformer can learn the pattern, right? Now, how do you label your training data during the fine-tuning step of named entity recognition? So let's take this sentence. I'm going to show you that first, and then we'll get into the code and the actual design. So let's say that your training sample looks like this. John shade an orange with Matt. Okay. Now, what you would do is look at each of those words, and then you would say, okay, John is a person, orange is a fruit, and Matt is a person. Assuming that you're interested in extracting the entities like names of people, whether something is a fruit or not, or names of companies or names of city and things like that. Okay. If that were the case, you would do it this way. And then the typical nomenclature in which you would record this for a named entity recognition use case is called as a BIO tagging scheme. So what that would mean is that this would actually be represented as, okay, John is represented as using a tag called B underscore PER, which stands for B underscore person. I'll explain what B prefix means. Okay, and then if there is a token that is not an entity that is of interest to you, because remember, you are determining based on your use case, what are the entities that you would like to extract? And here we are saying for this use case, I'm interested in extracting names of persons, names of fruits, names of cities, and names of organizations. So clearly shade and an are not any of those entities. So you'll say, okay, they are not. So I'm going to denote them with a tag called O. I'll explain what O is shortly. And then you'll go to orange and you'll say B underscore fruit and so on. So this is how you will tag. Now, what happens if you have a text block like this? Jane Smith, who lives in Seattle, reads the New York Times every morning. Now, using the scheme that I just showed you, you would start labeling it as the following. Jane is a person. Smith is also a person. You're not interested in you're only interested in a few set of classes of entities like names of people and city and so on. So who and lives is not any of those entities. So you skip that. Seattle is a city. You'll label that and keep going forward. And then New York Times is an organization. So you'll say org. Now, if you were to pass it just like this, you would just label it this way. The problem is that your LLM is going to learn it, but what it'll extract is it'll extract Jane as one person. It'll extract Smith as a different person. It'll extract New as one organization, York as another organization, and Times as another organization. You clearly don't want that because Jane Smith is the actual name of a person. It just so happens that it is split across two different words. New York Times is the entirety of that entity, one single entity called New York Times. It's not three different organizations or three different entities called New York and Times, right? So you need to have a scheme by which you can tell the neural network that there is a particular entity that spans multiple tokens. So that's where the BIO tagging scheme comes in. In BIO tagging scheme, what you do is you say, okay, let's start with this again, Jane Smith. So you'll first use this beginning of an entity. So you'll say begin, B stands for begin underscore PER, which means begin, this is the beginning of a tag or entity called person. The next token, Smith, is a continuation of the same entity. So you'll say I'm inside of the same entity. So it's going to be I underscore PR. So I stands for inside, B stands for beginning, I stands for inside. Then you go to the next token, who, and that is not part of the same entity. So you'll say, okay, I'm O, which means I'm outside of that entity. Okay. Anything that is tagged as O is a token that is not belonging to the entity that you're interested in extracting. Okay. And the same applies to things like lives and in and all that. Okay. Now you get to this word or token Seattle. Now you're going to say begin of city because that's a city and you're labeling it that. And it does not have any continuation. So you'll say, okay, that's fine. Now I'm outside of that entity. So reads becomes O, the becomes O. Now you get to New York Times, then you'll say, okay, this is the beginning of this entity called organization. So I'll say B underscore org. York is a continuation. I'm inside the same entity. So I, which is inside of the same organization. Times is also a continuation, so I'm still inside of the same organization. And then when you get to every, you're outside of that entity. So you're going to call it as O, and morning is also O. So this is how you would label your data for fine tuning for named entity recognition. This is a very popular scheme. Yeah, it looks cumbersome, but it is a pretty popular scheme. It's called BIO tagging, and you define the entities and you would use B underscore that entity name and I underscore that entity name to mark the boundaries for where the entity starts and how it continues. Okay. And you would give each of those tags or labels an ID, a unique ID. Okay. So this is how you would label for fine tuning your data set for performing named entity recognition. So before we get into the implementation of the transformer for solving NER, maybe one way of looking at making this simple is just build maybe a very simple web app where you would show a bunch of text and then you would let a bunch of team members go and highlight individual words or combination of words and then mark them as okay, these set of words means this entity and all that, and then store that. It should be pretty easy to build a web app like that. So that can kind of make it easy for using a crowdsourcing kind of a scheme to go and have your entire team participate in taking a bunch of text that you have that you want to fine tune on, and then get your labeled data. All right. Okay. So now let's go and see how you would enhance our large language model for solving this problem. So here you have your pre-trained encoder-only LLM, something let's say like BERT or so on, and you have identified that these are the type of entities that you would like to extract for the specific use case for which you're solving. I have n different entity labels. Remember that for each entity type you need to have a big N as well as a I, b underscore as well as I underscore. So each entity has two tags. And if a token is not part of an entity, it's called O, which is not an entity. So you also need one for that. Anyway, for this use case, I have 9 entity labels. In your use case, you could have more or less or whatever it is. Okay. Now, what you want to do is you want to first look at first of all, for each training sample, you've provided this. And the way you typically provide this is the text that you are passing in, let's say is John 8 in Orange in New York. And you would also have to pass the label for each of those tokens. Okay. So here, now I'm training my large language model. John 8 and Orange in New York. Okay. First thing I do is I tokenize it. So John 8 and Orange in New York. And I add the padding token so that I can fill up my entire context window. Okay. Now, just like in the past examples that I shared, you're going to prepend all this with a special CLS token, which stands for classification token. Clearly, because this is one type of a classification problem. You're trying to classify each token into one of its entity IDs, correct? So your input specific formatting is going to be prepending it with CLS. And let's say your input is an S cross D matrix. S again is our sequence length and D is the dimension for each of those tokens. Okay. Now, what is the ground truth value that you pass? The ground truth value that you pass is for each of those tokens. How many tokens do you have? What is the total S, the sequence length, maximum sequence length? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have about 10 tokens, right? So you have to create an array of 10 slots, and each of those slots will represent entity ID, the label ID that you're assigning for that token. Now, for the special tokens like CLS and PAD, I'm using this number called -100, and I'll explain why I do that shortly, but just go with the flow. Okay. For special tokens, I'm using some ID that is not part of this list here. Okay. Now, the first token, which is a valid token, John, right? Which is the sentence is John 8 and Orange in New York. John is what? You're labeled this as a person. And what is ID for person? Because neural networks do not understand text. You have to pass numbers, integers, or numeric format data. So what is the ID for B underscore person? It is 1. So Y true 1 is 1. 8. Okay, 8 in my data set, my training data set says is O, which is outside of a token. What is the ID for O, which is 9? So I put 9. The same thing for Anne. Okay, when you get to orange, orange is tagged in my training data set as B underscore fruit. What is the ID for B underscore fruit? It is 7. So I put 7 here. And N is also an outside of a token. So it's 9. Now, New York is one entity that I'd like to extract as. So in my training data set, new is tagged with B underscore city. What is the ID for that? B underscore city is 5, and York is I underscore city because it's a continuation of the prior token, and I underscore city's label ID is 6. Okay, 6. And again, pad is again a special thing, so I'm using this special number called -100. I'll explain why I'm using that shortly. Okay, just go with this flow. Okay, now you have into your neural network or into your LLM, you have your input and you also have your ground truth value. Now you pass it through your LLM, and what does it produce? It produces an S cross D size matrix. S is the total number of tokens in your sequence, and D is the total number of dimensions. Now, what is it that you want to do? Okay, what you want to do is for each of these words like John 8 and all that, you would like to emit whether it is one of these 9 entity IDs, correct? Now, you're taking an S cross D and you're saying for each of this slot in this S row, in each of these rows, you would like to emit one of these 9 values. N is, let's say, representing 9 here. N is the number, right, of IDs that you have. So you will need to have, you need to have a way to take this S cross D and produce an S cross N matrix. Because if you were to produce an S cross N matrix for each of these slots in S, right, each of the columns represents the specific entity ID, right, or the label ID, correct? if you can make a matrix like this, what you could do is that you could use softmax and you can figure out which of these entity IDs applies to each of these tokens. Correct? Let's say for John, you softmax it and then you produce ypred, and that is when you pass the softmax, if you remember, right, it'll distribute everything into percentages, and you send it through argmax and it'll pick the one that has the highest percentage. So let's say it picks B underscore person, which is great. For 8, let's say it picks O, which is outside of the token. For Anne, it picks city. Again, it is not a city. We know that because the ground truth value says it is not. But that's fine, because until it is trained, it is going to produce wrong results, and over back propagation, this will get fixed. But at least now that if you can take what comes out of your large language model, which is a contextual embedding matrix, which is S cross D, and if you can figure out a scheme by which you can convert it into an S cross N, where S is the total number of tokens in your sequence and N is the number of labels, then you can use softmax to figure out what label to apply, correct? Now, how do you do this? It's pretty straightforward. You use, again, a task-specific neural network. In this case, the task is to label. So I'm going to use a feed-forward neural network. I could actually use a simple linear transformation also, which is just one layer instead of 2 layers of a feed-forward neural network. I typically tend to like to use feed-forward neural networks because it gives you more weights and it will allow you to train. In case your data set is more complicated, it will allow the LLM to learn more. Okay, that's why I've been using FFNs instead of just a simple linear layer. Okay, anyway, so let's say I'm using a 2-layered feed-forward neural network. The first layer has weights D cross P. So when you take an S cross D and you multiply it with a D cross P, you will get an S cross P. Now you want to get an S cross N, so the second layer should have a P cross N, because if you take an S cross P, which is this one, and if you were to multiply it with a P cross N, you can get an S cross N. S cross P times P cross N is S cross N. So this is cross N. Now you have this. Now you have built your NER specific entity head that goes on top of your LLM, and this will allow you to train it so that you can extract entities from your blocks of text. You have not written a single regex. You have not written a single rule manually. All you have done is you have just labeled data and you're giving it to this large language model, an encoder-only large language model. And this large language model, with the combination of its understanding of language semantics that it has learned during pre-training, how humans deem to put different entities in the language, as well as this feed-forward neural network, it can start extracting entities. Okay. Now, actually, what happens here is that you have to measure the loss because you have emitted something here. So the loss is using what? Softmax. So the loss is going to be a cross entropy loss, right? Across this ypred 1 through ypred 7 and y true 1 to y true 7. Now, let me come back and explain why I've used -100 for these special tokens. The reason I use this -100 for these special tokens is because later on when I show you the code, I'll show you that there is a way in which I can tell PyTorch when it is doing a cross entropy loss that if you see a token ID of a certain special number, then ignore that in computing your loss. Now that is critical because you really don't care for this CLS token, nor do you care for these padding tokens. You don't want them to influence because you're not really learning anything. You're not really labeling anything. You're not extracting entity from pads or their CLS tokens. You're only extracting entities from the given text that is going into your LLM. So which means that you have to not account for these losses which are incorrect in your total loss calculation. So there's a way in which you can instruct PyTorch to do that by telling, okay, if you see a specific ID, then do not use that in calculating the loss. And I've just used -100. You can use whatever it is. Ideally, you have to use something that is not part of your entity ID numbers. Okay. So usually it's never going to be negative. So take any negative number. I'm using -100 just as an example. Okay. So that's how you would compute your loss. Once you compute your loss, what do? You go and backpropagate. You backpropagate first to adjust the weights in the feed-forward neural network. Then you come back and adjust the weights in all the encoder blocks of your encoder-only LLM and so on. And across multiple epochs, you run this through, and when your loss converges down to a very small number, you have LLM that is now pre-trained for doing named entity recognition. Okay. Now let's look at an implementation of this. Now in this implementation, I will train my LLM, fine-tune my LLM to take a block of text, and I'm going to prepare my data set so that there are some entities that I'm interested in extracting, it'll extract those. Okay. Now, the general code structure remains the same as what I've shown in the previous demo, which is think about it not just as a kind of way to kind of break up the problem. You have 3 steps. Step 1 is you want to build your custom model based on top of a pre-trained large language model already. Then the step 2 is that you want to prepare your step 2, you're fine tuning, right, which you're training with your specific data. So you're going to fine tune for named entity recognition. So you're going to first prepare your data set, which is getting it all together, labeling it. Then you actually run it through the fine tuning loop, where you pass it through your NER specific large language model, and then it adjusts all the weights, and then you save that entity, the fine-tuned entity extraction model, and then you get to the third step, which is you're going to use your custom model in your application. So once it is saved, you can take that saved model, you can move it to your production server, and then you load it up over there, and then just give it text, and then out comes the entities that it has learned, and it'll give you the values. Okay, now let's go and see a demo of this. I've implemented a Google Colab notebook to demonstrate how to build your custom model for doing NER. Okay, so first thing is I'm going to import the Python modules that are of interest to me. I have PyTorch, I have the Hugging Face Transformer library and scikit-learn and all that. Okay. Then next is I'm running it in Google Colab notebooks. I'm going to mount my Google Drive because that's where I've stored my data set, and that's where I'm going to download my pre-trained LLM. And I'm also going to save my fine-tuned LLM there. Okay. And in this case, in this demo, what I'll do is, in the previous demo, I use BERT base uncased as my pre-trained LLM. In this case, I'll be using Electra, which is pre-trained using the RTD strategy. Okay. All right. So if you notice, what I have done here is my data sets are here in this location. My pre-trained model is this here, and I'm going to be storing my fine-tuned model here. Now, question is, how do I get my training data? There are several online repositories for NER data. I'm going to be using the Wikipedia data. So somebody has put in the effort to go and tag everything, right, and across different languages. And in fact, there's a paper called Multi-Nerd, which they show all these things that they have done. And I'm going to use just the English one, which has 164,000 sentences, about 3.6 million tokens in that, of which there are 75,000 or some such number of people names in it, and 33,000 organization names, 78,000 of locations, and so on. Okay, if you just look at the data set here, I'll just show you a very quick one. The way they have tagged it is, so they have taken each word and they have labeled it as O or B underscore person and so on. Okay, so they put in quite a bit of effort, so we should thank them for that. Okay, so that's that data set. I mean, there are many such data sets out there. Like, for example, MIT has a very popular data set on movies. For example, they take different types of things from movie domain and then they tag each of those tokens. Like, what movies star Bruce Willis are tagged as OOOs outside of token, outside of entity, and B underscore actor for Bruce, and I underscore actor for Willis, and so on. Okay. Anyway, so different data sets are there, and you could build it up for your own specific data set. For now, I'll use Wikipedia because it captures a good amount of data as well as it is for generic English type sentences. Okay. All right. So now that is done. Now I'm going to show you how we build our custom entity extraction model. So I have defined a entity extract entity model. So this is my class. To the class, I initialize it by passing the model name, which is the pre-trained model name. In this case, it's Electra. I also pass the total number of tags that are entities that I'd like to extract. So let's say we call this N. Okay. And here I'm downloading from Hugging Face my pre-trained model, which is an Electra model. So this is going to produce a context-aware embedding matrix, which is size S cross D. Again, S is the sequence length and D is the total number of, right, for each of the tokens. So this hidden size is D. Okay. Now I have here my task-specific neural network head, which is a FFN, a feed forward neural network. The first layer here, as you can see, is a linear layer. So what I'm doing here is, let's say what comes out of my transformer is S cross D. Okay. I'm going to pass this through to my FFN, correct? Now the FFN has 2 layers. The first layer has a D cross D matrix. In the previous slide, I showed you something bigger than that. I mean, I show you a D cross P. But typically, I've seen you could use a D cross D also. It's fine. If you want to, if you have complicated text, complicated entities, then you can use a P here, and the P could be 4 times D. That's fine too. Okay. Anyway, so this is the first layer is going to have this. This is the first layer. Then it goes through a ReLU, which gives you the non-linearity, which is the activation function, which you see here. then that I will send through my second layer, which is here, and that is how much? Hidden size, which is D cross number of entity tags, which is what? N. Okay, this is what it is. So now if you do this, what happens is when you take an S cross, so when you take a S cross D that comes from your transformer, you multiply it with the D cross D, which is the first layer of your FFN, that produces what? It produces a S cross D matrix, correct? Now you send that to your ReLU, all right? And that will again still be an S cross D matrix. Now you take that S cross D and you multiply it with your second layer of your FFN, which is D cross N. Now you have your S cross N matrix, correct? This is what you have. That's it. So now that you have your S cross N, you're good to go. I can use my cross entropy loss function, right, to figure out for each of these S, which is entity label that you'd like to extract. Remember, I said that I'm going to use something to tell my PyTorch cross entropy loss function to not include those tokens in the loss calculation that have a specific ID, the special token, the CLS and the padding token. I'm just saying ignore any token which has a token ID of minus 100. So later on at some point in the code, I should actually pass minus 100 for CLS and for padding. So I'll show you that. But this is where that thing kicks in. Okay, so you're telling cross entropy loss, do not use that tokens logic for calculating loss. Okay, anyway, so in the forward pass, what you would do in your method here is you would get your inputs, which is, let's say that the input is going to get, let's actually write that here. So let's say that the actual text was John lives in, let's say, New York. Okay. All right. And what you would get is the tokenizer would have given you, tokenize it as CLS followed by John, followed by lives, followed by in, followed by new, followed by York, right? Let's say it does that. And then what you would actually get, because neural networks only understand numbers, is the token ID. So let's say the token ID for CLS is, I'm just taking some number, okay? So let's say it is 5,000 or something like that, okay? For John, it is 23. For lives, it is 43. In is, let's say, 8. And New York is, let's say, 90. New York's 90, and then York is, let's say, 23 or, sorry, 20, so 89 or something like that, okay? And of course, you'll also have pad. Okay, let's just say we do pad also. Pad, and pad, let us say, is also has a special token. Maybe it's 0. Let's say it is 5001 and 5000. Let's say it is that, okay? Now this is what will be your input ID. So input ID that you see here is going to be this, okay? Input IDs is going to be this. Now what is attention mask? Attention mask, actually let me copy this here. So attention mask is, right, which is this one that you see here, is you do not want your LLM especially in the self-attention module to pay attention to the pad tokens. I mean, especially when let's say your entire transformer was trained on 512 tokens as your maximum sequence length, and your sentences that are coming in are much smaller, you would have a lot of pads, and you don't want that to dominate in self-attention calculation. So the attention mask, all it does is it uses one if it's a valid token, and if it's one for another valid token, and so on. Or whenever it sees a pad, says 1, 2, 3, 4, 5. So 5 ones. Then for pad, it will pass 0 and 0. So it gets masked out during the attention calculation. That's all it is. Okay. Anyway, so in the forward, you get that, you pass this through your transformer, you get the output from that. In the output, you figure out the last layer, which is here you would get your S cross D matrix. Okay. S cross D matrix. Now that you pass through your NER classifier, right? That S cross D, and NER classifier will do what? It will execute this logic here. It will go and run it through this feed forward neural network. It will produce the logits, and that logits, remember that in PyTorch, the forward method is called both during training and during inference. If it is called during training, the white row is passed. So the white row is passed through label. So it is non-none. So then you would calculate the loss. You'll calculate the loss with what? The predicted logits, which is NER logits, which is here, and the white truth, the ground truth value, which is coming in through the labels. Okay. So that is what you're going to pass through which loss function. The loss function is defined here, right, as cross entropy loss function. Once you get that, you send the loss back in this dictionary, and you'll also send the logits that you get out of your FFN through this. Why do you do that? This is not needed during training. Only during training, what you need is loss, because the loss is used to backpropagate the loss and fix the weights. But during inference, there is no loss because labels, you're not passing any ground truth value. So labels is none. So what you get called is just with this, and you want the actual logits to be passed back so that you can look at those logits and emit out the textual names of the labels that are associated with this each token. Okay. All right. And then of course the methods to save my custom model and then load it up later and so on. Okay, so let's execute this code. Okay, that's done. And I have a few other functions that I'll show you shortly, but let's just go with this. Okay, let's just keep going, keep going, keep going. I have actually downloaded my model, so I'm not going to be running it again. Fine tuning takes time, so I'm not going to be doing the fine tuning as well over here. But I'll just show you the functions, and by the way, I'll upload this into my GitHub repository so you can download this Collab notebook and play with it yourself. So I have this function here called prepare dataset for fine tuning, which is this one that you can see here. All it does is that you can give it a CSV file or a TSV file or what have you, and it'll parse it, and then it'll extract all the entities, and it'll prepare the Y true and corresponding X and all of those things. Okay, that's all it does. Because the format that you notice here is different than, for example, the MIT format has it in this, the Wikipedia format is slightly different. So you really don't want to work with different formats. So what I've done is I've implemented a function that will, depending on the data set, it will go and cleanse it up, and it will do things. It will prepare it in such a way that the rest of my code does not have to worry about whether the tags come first or the tokens come next, or the tokens come first and the tags come next, and all that. There's a little bit more logic here. Like, for example, let's say this is an important thing to understand, so I'll explain it. Let's say that sentence that comes in is, I live in California, right? Remember that this could be tokenized as I, comma, live in such as 4 tokens. However, when you send it through your tokenizer, it could actually tokenize it as follows. It could tokenize it as, sorry, I live in, and Cali is one, and then Fornia is another one. But in my in my CSV file, maybe this is tokenized as, one second, let me explain it here. Let's say this is tokenized as outside of token, not interested, outside of token, not interested, token, this is also outside of token, right? And this is B underscore, let's say, location. Okay, this is what it's tokenized. This is how I'm recording it in my training data set. But when you pass it through a tokenizer, you notice that some tokens can be actually split by the tokenizer into different components. So which means that I need to write some code that would actually set up my Y true as follows: B underscore location and I underscore location, this one. So this function takes care of doing all of that stuff. Okay. Anyway, that is that. Okay, now the training data set, it's loading it from the Wikipedia. It says, okay, there are 33 different entity types, and there are about 118,000 samples here that I'm going to use for training, and 13,000 samples for validation. Okay, so now I'm going to build the entity model here, now my NER model here, and then I'm going to fine tune it. I've already done that. It takes time, so I really don't want to show that again here. It takes about 40 minutes to train. Run it across 3 epochs. I think the loss is decently small, so which is good. That's a sufficient amount of epochs. And okay, so let's see. Actually, let me just show you this fine-tuning entity extraction model code once. Okay, where is that? It is here. Okay, this one here. So what this does here is it takes the training data set and the validation data sets, the number of epochs. It'll take my model. We set up some location where I'm going to say my checkpoints. I'm going to set up my training arguments. I've already explained this in the other use case. I'm not going to go to the details of this. And then it just calls the trainer method, and it passes the model, which is my entity extraction model. Remember this one here, It'll pass that. Okay. And it'll pass my training arguments, my training data set, and then the collate function I already explained in the previous example. The Hugging Face transformer is only designed to take in the input ID, token IDs, as well as the attention mask. But I'm doing this for my own use case called named entity recognition, which requires the ground truth values also. So I need to pass a label. So the collate function actually helps in telling the code that this is going to be my ground truth value. So that's how I pass using the collate function. And then I call trainer.train. That's all I'm doing. Okay. All right. So I told you that I already fine-tuned it. So I'm going to skip that now. This is all, this is what it is. And I've saved it also. Okay. Now let's go to the inferencing code. Let's just focus on that. Let me hide this. Okay. So the inferencing code, what I do is I load my saved model. Okay. So I'm going to load that. Okay. So it loads my fine-tuned model weights. It'll load all the fine-tuned LLM the base transformer weights, it'll load my fine-tuned tokenizer, vocabulary, all of that stuff. Because during fine-tuning, I could have introduced new tokens also. So it's also going to load that. Okay, now what I've done is I'm going to give it a block of text, and I have a series of sentences here, like capital of India is New Delhi, just like Paris is for France, and Washington DC is for USA, and so on. Tom Hanks acted in a movie Castaway in which he was lost at sea. And I'm going to run that through this small utility function called extract entities from text. Okay. And all this does is that for the tokenizer that I've loaded up from my saved fine tuning step, as well as my model, it'll pass it to that model. It'll actually tokenize each of these strings and then pass it through the model and the tags, right? The numeric tag IDs and all that stuff, so that I know the mapping between, because the transformer will only produce numbers like 1 and 2 and all that. I need to translate and put that when I'm presenting it back to you. I need to show it with these human readable textual information. So I just pass that as well. Now let's run that. Okay. So when I run it, okay. So for this text, capital of India is New Delhi, just like this. He said the locations in this text is India, New Delhi, Paris and France, Washington DC and USA. Tom Hanks acted in the movie Castaway, in which he was lost at sea while on a FedEx plane. So it says, okay, I think it says, okay, there's a person named Tom Hanks. Two different words, but same entity, Tom Hanks. And there is an organization called FedEx. Okay. Next one is, let's say Steph Curry plays for the Golden State Warriors, a basketball team in United States, which was earlier owned by Vivek Ranadive. So it says, okay, I can see two person in this text, Steph Curry, two different words, but it's instantly recognizing as one. Vivek Ranadive is another person, and Golden State Warriors is the name of an organization straddled across three different tokens, right? Let's say I take this, Partha Sitala, that's me, who lives in Los Altos Hills, flew to meet. I'm going to give it, just to trick it up, I'm going to give a name that most likely it's not there in Wikipedia or anything like that, which is Sheikh Abul bin Sultan al Hakimul Khan, spread across so many different words. It has all these hyphens and whatnot. And we want to show here that without defining any rules, explicit rules to extract, just by understanding language, what words appear around entities and all that stuff, it should extract this as one single name, right? And it did. It says person is me here, and it also says person is this one. I think there's a bug. It should actually call it a shake. I think the bug is not in the neural network logic that I wrote. It's mostly in the correlating multiple tokens to print it as one. I'll fix that later. Anyway, so even location, Los Altos Hills is traveled across three different words. It's picked it as one, so and so on. That's amazing. Now, it's not just one small piece of text. I can actually give it very large pieces of text too. So what I've done here is I'm going to point it to some online article, okay? And I'm going to download that article from the internet. I'm going to extract the text out of that. And then I'm going to pass it through my another wrapper function I wrote. And this wrapper function is because remember that I've defined my sequence length to be only so much. Let's say 128 or something like that. That's what I've defined my model was defined so that it will take up to 128 tokens max. But your article will have definitely much more than that. And remember, you're giving the entire article. So all this function does is takes this entire stream of text that you've downloaded and chunks it up into something that is no more than 128 tokens at a time. Okay. So let's run that. Okay. So here it's downloaded, and then it says, okay, the people that I see in this article is Sam Altman, Samuel Harris Altman, and so on, Oliver Mulherin, right? And so on, Paul Graham, Elon Musk. The locations I see is Indonesia, Netherlands, Chicago. Organizations I see is Wikipedia Commons. I don't know why it calls for institution, Apple Macintosh, but it shows that. I mean, this is interesting. For time, it shows inauguration is actually identified as a time, right? Which is kind of very interesting. So this is pretty cool. Just by looking at text, it is able to extract entities without writing any manual rules. I think that's very, very powerful. All right. Now I'm going to show you a fourth type of a use case that you could solve using encoder-only large language model. So in this use case, what we'll do is the problem we're trying to solve is given a sentence or a paragraph or an entire block of text like an article, you'd like to retrieve similar text from our repository. Okay. Now, what is it used for? What is a practical real life use case for something like this? Let's say you're building a customer support ticket portal, and when a ticket is opened, you'd automatically like to go and say, okay, there were other similar tickets based on the content that I can recommend that you look at, so that you can solve the problem yourself. Or similar to that, a knowledge base article, right? Where You're putting in things into your Confluent, let's say wiki, and when somebody is looking at that, you could go and say, hey, these are the other things that are similar to the thing that you're reading right now. Quora, for example, the popular Q&A online web service site, they show you when you're reading a question, it can show you similar things. Perplexity, for example, when you're asked a question, it can show you similar things as well. So there's so many things that you could do with it. You could do bug track. Your software QA team has opened a bunch of bugs, and the dev would like to know, is it a dupe of something else? And you want to do all that based on not just the text, but you also want to do it on based on the semantic similarities between two different text blocks. This is a mock-up of a screen that shows a bug tracker or a triaging system that when a bug is opened, it will show you that, hey, this bug seems to be similar to the previous ones that are already open. Okay. So what does it mean to actually say text is similar? Okay. Now, for example, how do you typically find things? We find things by doing keyword searches. Okay. Let's say there are two tickets. Ticket A is Excel crashes when saving large files with macros. Ticket B is my laptop crashes while opening large files and fan overheats or something like that. If you were to build a system which is just looking for keywords like crashes or large files, then it will say, okay, these two seem to be similar, these two tickets, but they are not. The first one is related to, yes, it is crashing in at large files, but it's an Excel related problem. And the second one is it's a laptop related problem. They're completely dissimilar, right? And let's take another example. The other example is where keyword matching will not work is ticket A says app crashes while exporting my docx file to another format. And ticket B says Word isn't responding when saying my file as PDF. Here, there's no keyword that matches. But semantically, we know as a human that both these tickets are related. Okay. So, how do you build a large language model that given these two blocks of text or more blocks of text, it will say, okay, this is a similar and this is the scoring I would give for similarity, or these are dissimilar. Okay. Now, remember that in previous episodes, I told you that you could determine similarity of words just by looking at word embeddings. So if you can extend that from word embeddings to sentence or paragraph or a block of text embedding, then can we use the same strategy of doing cosine similarities and then determining if blocks of text are similar or not? But of course, for word embedding, you say that each word has different features and you would score like a word like apple has features like fruit and company name and taste and color and so on. And for each of those features, you can give it a different score. And word to vec and glove and all these things will determine that automatically for you. How do you do that for a sentence? What are those features? You don't know what those features are, but how do you come out with these dimensions that will grade or give scores for entire blocks of text? Okay, so couple of strategies are there. Number one, you can say, okay, let's say that I want to do averaging of the token embeddings to determine a sentence embedding. Okay, so for example, the sentence is she alone finished the task and it has, let's say, d dimensions each token. So you do something like this, and you can say, I'll do my sentence embedding by averaging the embeddings for each of these tokens, for each of the, averaging out for each dimension. For this, you take, let's say, dimension one. Across all the tokens, you'll average out, and then you'll store that for that dimension for that sentence. Okay. Go to dimension two, average it out, and so on. So you construct it this way. Now, the problem with something like this is if I change the word order, let's say she alone finished the task, I change it to she finished the task alone. We know that these two sentences are not meaning the same thing, although they share 100% of the tokens with each other. Their meaning is semantically very different, correct? But when you do an averaging across the same dimension across all the tokens, the average would be the same because the average does not really care for the ordering of the words. So this strategy will not work. What happens if you do it the other way? Instead of doing it on a column by column basis, let's say you do it on a row by row basis. Okay. So I say, okay, she, I'm going to average it across all the dimensions of she, and then I'm going to take alone and average it out across all the dimensions and all that. I can make this my sentence embedding. This is good because even if I change the word order, right, my embedding changes. The reason the embedding changes is embedding also has its ordering like this, correct? This way, correct? So let's say she alone finished the task will have something like this, and she finished the task alone. The embedding for alone would appear as the last row. So it will be different. The limitation is that, okay, this is going to give you, it overcomes the problem that I showed you by doing average pooling across the same dimension across all the tokens. It overcomes that. But there is no way to still tell that there are two sentences that do not share the same words but mean the same thing. For example, she alone finished the task is semantically similar to something like Lisa is the only one to complete her assignment, right? Now, you want to build a neural network or a large language model that can say that, okay, these two things I think mean the same thing, and this is the scoring I would give for how similar they are. Okay, that is what we'll learn now. Now, this I'm going to be using in subsequent slides. I'm going to be using the word pooling. Pooling nothing means here. Pooling is a strategy in which you kind of collate things and all that, right? So in this context, pooling means I'm creating a mean pooling of the embeddings for each of the dimensions for a token this way. Okay, that's all it means. Okay, all right. Now, so very quick recap: in a self-attention, you're using the technique where your large language model or a transformer is trying to determine how it will change the individual dimensions of each of those tokens, feature dimensions of each of those tokens, based on the context in which these words appear, right, in the sentence. Similar to that, you want to build a different type of a transformer. Let's say you call it, so that transformer is called a sentence transformer. And that transformer, what it does is it figures out a strategy in which it can swing the embedding matrix for entire blocks of text, whether it's a sentence or a paragraph or an entire article, in such a way that you could do similarity measurements across different blocks of text. Okay. Now, this sentence transformer was published in a paper called Sentence BERT, and it proposes a strategy called Siamese network that you could use to fine tune a encoder-only large language model, a pre-trained encoder-only large language model, to generate sentence similarities or sentence embeddings that can be used for doing sentence similarities. Okay. So I'll tell you how you would build a Siamese network based fine tuning strategy. So let's say that I'm fine tuning here. So which means that I need to label my data. So what I would do is I will create a training data set where I'm going to take two sentences, sentence A and sentence B, and I will painstakingly create a similarity score myself as a human deems how similar they are. Okay. And let's say the score is a value between -1 and +1. Okay. Now, what I do here is I take this first sentence and I pass it through my pre-trained LLM, encoder-only LLM. Let's say BERT. Okay. Now, that's where my sentence goes in. Then this is going to produce what? It's going to produce a context-aware embedding for sentence A using the mean pooling strategy, which is, let's just go back here. It uses this strategy here. Okay. So it's producing this. Okay. All right. Now, what I do here is, this is the mean pooling. I'm going to take this mean pooling and I'm going to call this U. Okay. Now, this is the head that I'm attaching on top. Let us say the head that will first of all do mean pooling. Okay. Of all the tokens here across their dimensions. Now, Siamese network. Siamese network means something is joined together, right? So what it means here is that now you take the second sentence and you pass it through the exact same LLM. Exact same LLM. These are not two different LLMs. You pass it through the exact same LLM and it'll again generate the context aware embedding matrix for sentence B, and you do the mean pooling and you get that mean pooling into something called V. Okay. The first sentence is you're pulling it into a variable matrix called U, and the second sentence you're pulling it into a matrix called V. Then what you do is that your head on the top will do a cosine similarities between these two. Okay, U and V, and that the value is going to be between -1 and 1. Okay, a cosine similarity of 1 means they are the exact match. A cosine similarity of -1 means they're opposites to each other, and if the cosine similarity of 0 means they are they do not have any relationship at all. Okay, that's what it means. So this is how you're going to build it. You're going to build a neural network this way by doing mean pooling, and you are going to use a Siamese network strategy of taking two sentences, generating their independent mean pooled sentence embeddings, and then run it through cosine similarities and produce one output. If this output that you produced is differing from your ground truth value that you pass through your training data set, you get this loss, you propagate that loss back, and then you adjust the loss in this head that you have here and the LLM as well. Now, one question is, as humans, if you want to label things a value between -1 and 1, it's very hard. Is 0.9 and 0.8. How different or how similar or dissimilar are they? It's very hard to say. So typically you can use a binary thing. Do you think sentence A and sentence B are similar to each other? If you think they are similar or somewhat similar, mark it as true, which is a value of 1. Do you think sentence A and sentence B are similar to each other? If you think they are not, then just mark it as false or a value of 0. That is simpler. But when you do it that way, you cannot use cosine similarity. You need to use some other strategy. So this paper proposes an alternate strategy. If you have, let's say, you want to encode it as a true or false, whether the sentences are similar or dissimilar, you use the same strategy. You do the same mean pooling, and for the first sentence, you call it U. You do the same mean pooling for the second sentence, you call it V. But then you create a concatenated matrix, which you take U, which is this one, you take V, which is this one, and then you take a subtracted value of U minus V. You concatenate everything, and then you pass it through a softmax across two logits, right? 1 and 0. 1 means similar, 0 means not similar. And then you calculate the loss, and then you do a binary cross entropy between this as well as what you're passing as ground truth value in your training data set. Okay, so that is what you would do. So this is called as a sentence transformer, and what it produces is, given two sentences, it will tell you how similar or dissimilar they are. If you're using fine-grained similarities like cosine similarity strategy, or it will give you a binary output. They are similar or they are not similar. Okay. Now let's see a demo of how you would go and build this. Before we see a demo, I'm going to give you a general strategy of how to build this, to build an end-to-end similarity recommendation system. A similarity recommendation system could be something like, let's say, Stack Overflow or Quora or your own knowledge base, where somebody asks a question, you want to look at that question, and then you would say, okay, there are other similar questions or topics that are similar to the question or topic being asked or queried. Okay, that's what you're going to do. So what you need for that is, step one is that obviously you want to fine tune your encoder-only LLM using the Siamese network strategy. Okay, so which means that you need to have a training data set that is already labeled with two sentences and whether they are similar or not, and so on. The next thing is that you also want to build a vector database of embeddings. Okay, what does that mean? What you want to do is, once you're done with your fine tuning, you want to take all your existing data in your, let's say you're doing this for knowledge base, or let's say you're building this on top of Stack Overflow. So you'll take all the questions that are used on Stack Overflow, those blocks of text, you'll pass through a fine-tuned embedding. And what does a fine-tuned sentence transformer give you? For each sentence, it'll give you an embedding, sentence embedding, correct? Sentence 1, embedding 1, sentence 2, embedding 2, sentence n, embedding n. Now you would like to store all these embeddings in your vector database. Why do you want to do that? The reason you want to do that is you would like to get a mapping between a sentence in its text form to its embedding value. Why do you need that? We'll see that shortly. Okay? Because when you have an embedding like that, later on, if somebody were to ask a question, let's say I'm calling that question a sentence queue, you pass it through this fine-tuned sentence transformer, it will give you the embedding for that sentence queue. Now you can you can query your vector databases and say, hey, take this embedding queue and match it across all the embeddings that you have. Let's say embedding 1 through embedding n, and then give me the text form of those sentences where there is a match between embedding Q, the query embedding, and what you already have stored. Okay, and it will give you, okay, sentence A matches your sentence Q, the query sentence you're asking, and it has a similarity score of 97%. Sentence K is similar to this query that you're asking, and a score of 83. And sentence M is similar, score of 81. And sentence L is similar, score of 78. And you can see, give me the top 20 or something like that, and it'll give you a scoring for each. Okay, how does the vector database go and figure this out and all that? That's a topic that I'll discuss in another episode, where the simplest way of looking at it is that it will do cosine similarities, but it cannot do a cosine similarities across tens and thousands and millions of sentences that you have in a vector database. It's going to be very slow. So there are strategies like hierarchical, navigable, small worlds. That's a strategy that you can optimize this lookup. We'll study that in a different episode. But the idea here is that if you can store it in a vector databases, they are designed so that you give it an embedding, it'll give you the sentences that are similar to this embedding. Okay, so we will use this setup, this 3-step setup, to build out something that will show similarities for a given query in text form. All right, now let's dive into our demo. So I've built a Google Colab notebook, and in this Google Colab notebook, I'll be showing you how to build a similarity recommendation system. Okay, and here the 3 steps are going to be slightly different from the steps I showed you in the previous examples, because what we do here is that step 1 is that we're going to fine tune our sentence transformer so that given a text, it can give us the sentence embedding. Step 2 is going to be to build a similarity database, which is take all the text from whatever data sources we have and then use our fine-tuned sentence transformer and get an embedding and store the text of that sentence as well as its embedding into our vector database. And then step 3 is the inferencing, where given any new text, it will load up the similarity model, which is a sentence transformer. It will load up our vector database, and then it will pass that text to the sentence transformer to get the embedding of this text and ask the vector database, hey, give me all the other texts that are similar to this. Okay, so I've installed over here. Okay, so here I'm installing the required Python modules, the sentence trans. I've already done this. I'm not going to run it again. And for vector database, I'm going to use this popular open source vector database called Fias. Okay, and then I'm going to import all my modules that I'm interested in. Okay, then what I will do is that I'm going to download this model into my Google Drive because I'm using Google Colab. By the way, the model that I'm going to use is this one here. This is a sentence transformer that's implemented in Hugging Face. It's called all-mini LM. You can go look it up. It's a pretty neat one. All right, so okay, let me run this. There you go. So the model name is this, and I'm going to download the pre-trained transformer into this location. The fine-tuned transformer I'm going to save here, and my vector database I'm going to store here. Okay. So the next step is to prepare our training data set. Now in the training data set, what I want to do is I want to use three fields. Question one is the text for question one. Question two is the text for question two, and is it a duplicate or not? Okay. Now there is a pretty popular data set called the Cora question data set where you could, in fact, let me just do this. Let me just show you only the relevant columns from this data set. Question one, question two, and is duplicate. Okay, let's say 100. This data set, they have multiple questions and they use a 0 or 1 scheme to say whether those two questions are semantically similar or not. So it's a binary representation. Okay. So for example, the question is, how can I be a good geologist? And question one is that. Question two is, what should I do to be a great geologist? They say, okay, these two questions are similar. Or the other one is, which one dissolve in water quickly? Sugar, salt, methane, and carbon dioxide. And the second question is, which fish would survive in salt water? They are dissimilar questions. So there's a pretty sizable set of two question pairs that they have gone through and captured it this way. All right, so that's what I'm going to load up here. Okay. Now, one thing is, okay, so that's all loaded up. Okay. Okay. Now, one thing is, I have implemented these functions that, for example, it loads up the sentence transformer. This is all pretty straightforward. There's a method, a library function called sentence transformer that Hugging Face provides. You just give it the model name and it'll load that up. I'll fine tune that sentence transformer. The loss that I'm going to be using is cosine similarity loss, and I will pass that to my sentence transformer. And I'll save the sentence transformer using the model.save, and I can later on load it up using the sentence transformer method and so on. Okay, actually, I'll come back to this code a little bit shortly. Now, I've already implemented the fine tuning step. It takes time, so I'm not going to be running it again. So the idea here is you prepare your training data set. All I'm doing is I'm downloading this Cora question pairs data set. I'm just cleansing it up, and then I am splitting that into training versus validation. So 90% of those samples will go to train my sentence transformer. 10% I'll use to validate my training or my fine tuning step. I load my sentence transformer here. I fine tune it, which is nothing but just passing each of those question pairs with their relevant score. And then I save my sentence transformer. It takes time. So I've already done it here. I'm not going to run it again because it just takes time. And let me just hide this here. Now, the next step, of course, is that once I have trained my sentence transformer, I need to build my vector database. Why do I need to build my vector database? Because I want to have a database of all the questions that were asked in the past and what is their individual embedding, so that later on, when a new question is asked, I should be able to consult this database to find out questions that are similar to the new question being asked. So I built that similarity database. Okay, the way I build that similarity database, let's actually look at that code. Okay, build similarity database. All the sentences I would go and then I would ask my sentence transformer to give me the embeddings for all these sentences. Okay. And then what I would do is that I would build an index, my FIAS index, which is I'm using FIAS as a vector database. And I will add all those embeddings, the sentence embeddings into my embeddings index. Okay. FIAS database. And then I will be saving this. I'm going to use FIAS.write index and I'll be saving it. Okay. Now, by the way, when an embedding is created, the sentence transformer will give me an embedding. I need to normalize my embeddings. You can go read that up offline, but the general idea behind normalizing is that you really want, remember that I told you that when you have these numbers which can have different magnitudes and all that, you really want to normalize all those numbers across all the dimensions so that across different embedding types, you really want to have you want to match normalized embeddings rather than match the non-normalized raw embeddings so that if the magnitude of one is more, it does not carry more value. I've actually explained this in multiple episodes, including episode 1 of season 3. So you can go and look at that too. Okay. All right, so this is the code to build that similarity database and then store that similarity database, which is a vector database using Fias. Okay, I've done that already, so I'm not going to be running that code again. As you can see, I'm storing it. It's done. All right, now let's go to the inferencing part. In the inferencing part, what I do is I need to do what? First thing I need to do is I need to load my sentence transformer. Why? Because when I give it a new query, I should run it through the sentence transformer so I get it an embedding back, correct? So I'm going to store my sentence transformer into model, which is a fine-tuned sentence transformer. Fine-tuned on what data set? The Quora question pair data set. Okay. And obviously, when you're implementing it for your own production use case, you would construct a data set, training data set, or fine-tuning data set with two texts and then a similarity score. Okay. I'm also going to load my vector database. This is my Fias vector database. Okay. Once I have loaded it, let me also load some from the Quora question answer pairs. I'm going to take some of those data, those questions, and I'm going to now check against my vector database if I have something similar. But the way I've implemented this prepare, training, and test data set is when I try to extract the testing sentences, I have not exposed those test sentences to my during my training or my fine tuning run. So these are all new sentences that my sentence transformer has not really seen. Okay. Anyway, so I'm going to load my data set that I'm going to now use during inference. So for each of those, I'm going to pick up about 10, okay, 10 sentences or 10 questions from my this Quora questions. And first thing is I'm going to run that through my model to find similar ones. And what does find similar method do? Let's just go and see the implementation. The find similar method, where is it? Find similar will take the sentence transformer, it'll take the vector database, it'll take the sentence and it'll say, okay, give me the top 10 similar sentences to this sentence that I'm passing as input. And the way I will pick the top 10 is I'll only pick those sentences that have a similarity score over 60%. That's my thresholding function. Okay. The first thing is I want to get an embedding for this sentence. The way I get the embedding is I pass the sentence to my model and that will give me an embedding which I normalize, okay, and I'll return that. So this is my embedding for this sentence embedding that I'm getting from my sentence transformer. Then I will give this embedding to my vector database and say search for this embedding and something that is similar to this embedding and return up to the top 10. Okay, it's going to do that. And then I'm going to say among the top 10 that you gave me, if there is a sentence that you're giving me that has a similarity score less than this thresholding value, which is 60%, then ignore that. Otherwise, I'm going to save that as a result and return it back. That's all the find similar method does. Okay. So now let's run this. So when I run this, actually, let's see this question. Okay, let's see this question. How close we are to see Third World War? Okay, that is a question. Okay. And it's saying that there are other questions of this type like how close are we or not close right now to World War III? And I think there's a 95.3% similarity. Or is the Third World War imminent? It says 93.9% similarity. Let's pick up something else. The question is, how do I improve logical programming skills? And it says that, okay, there's another question that was asked in the past by somebody else. And the question was, how can one improve his logical reasoning abilities? And I think they are similar by 81.3%. So I think it's done a very good job of identifying similar questions that were asked in the past for the things that I'm asking. I mean, look at this. How many hours a week do Google employees work? And it said that, okay, somebody else asked a similar question that you might want to look and answer for. The question that they had asked is how many hours a day do Google employees work on average? How much do Google employees get paid? It's showing things that are similar to the question you're asking. Okay. And these are all semantic similarities, not just doing keyword matching. Okay. So that's how you would build a duplicate detection or a similarity recommendation system using encoder-only large language model. And you would use, of course, a vector database to have a database of similar questions that are asked in the past so that you can retrieve and show them during query time, inference query time. All right. We have now come to the end of our episode 2 of season 3. Let's do a quick recap of what we have studied in this episode. The first thing I showed you is that an encoder only large language model, the way you would build that is think about it like two steps. Step one is that you would pre-train it using self-supervised learning, which means you don't use any human labeling. You download as much text as possible from all over the places that you can get for example, the entire internet, web crawl, and so on. You pass it to your encoder-only LLM and you pre-train it. In this pre-training step, the encoder-only transformer weights are adjusted so that by the time it is pre-trained using masked language model or RTD or next sentence prediction or sentence order prediction and all those strategies, what you would get is a pre-trained large language model that understands the context of the human language, how words fit together, which words do not fit together, how sentences come together, and so on. You take that and then you go to the next step, which is fine tuning for your task specific needs. Like a task could be classification, a class could be similarity detection, a class could be named entity recognition, and so on. So you would fine tune it using different strategies. So the next thing I taught you is how you would create a mental model of how you would build a encoder-only large language model. So there are four abstractions that you have to have in your mind. The first abstraction is how would you structure the input into your encoder-only LLM? Okay, so you start with an encoder-only transformer. Let's say your task at hand is pre-training. You would structure your input based on the training objective. The training objective could be masked language model, RTD, NSP, and so on. If you're doing pre-training using masked language model, you would take input strings, then you would mask out 15% of those input strings and pass it. The second part of the abstraction is going to be, okay, now you have your input going into your encoder-only transformer, which produces a context-aware embedded matrix. Now you want to adjust the weights in that transformer. The way you do that is that you would put a task-specific neural network head on top. For example, in the pre-training step, the task-specific neural network head is going to be a feed-forward neural network that will say, it will predict the masked words if you're doing MLM. Or if you're doing fine-tuning specific training, let's say it's classification, you would have again a feed-forward neural network that can figure out which classes this particular text that is coming in as input belongs to. The third abstraction that you have to have in mind is what is going to be the output function. So for example, if you're doing a multi-class classification, you would use softmax. If you're doing multi-label classification, you would use sigmoid function, correct? Corresponding to the output function comes the fourth abstraction, which is the loss function. What is the loss function? If it is softmax, you're going to use cross entropy loss function. If it is using sigmoid, you would use the binary cross entropy loss function, and so on. So generally, when you're thinking about extending what you have learned today for solving your own problems, I think this abstraction is very good. You have your encoder-only transformer, what it does. You have to figure out these four things specific to the task that you're trying to either pre-train or fine-tune your encoder-only transformer so that you can build an encoder-only large language model. Okay. Once you have done that, you can apply it towards the different types of problems that you have fine-tuned your model for. I showed you examples of classification. I showed you examples of labeling, entity extractions, and similarity and duplicate detection. There are other use cases like you could extract summaries. It's called extractive summarization. Or you could run it across question and answering, where you can do extractive question and answering. And there are several other use cases that you can build just using encoder-only large language model. Okay, so this has been a pretty long episode. I covered a lot of ground, but I'm hoping that you actually learned not just what an encoder-only transformer does or an encoder-only large language model is used for, but you actually learn the internal techniques of how you could take these ideas and then come up with your own strategies of maybe pre-training an encoder-only transformer to make an encoder-only large language model, or come up with your own strategies of fine-tuning it. Okay. Until next time, thank you very much. Subscribe to my channel, like it, and share it with others. Happy learning.